All right, welcome back everybody to part 2 of causality from prediction to action. I think, could we turn up the volume somehow on the magnification, because at this point my voice is beginning to strain after all. Is there any way? Thanks. Okay, so quick review of the material before the break. We decided that we're interested in estimating the causal effects of interventions. We wanted to know how will the outcome differ if I gave somebody treatment rather than control. Then we formally defined this class of questions as a contrast between potential outcomes. We noticed that we can never directly observe these outcomes, the potential outcomes that we need, and hence we can't directly observe causal effects. So, under what conditions can we nonetheless estimate causal effects? Well, either we could run a randomized experiment, and if you're lucky enough to be in a position where you could do that, do it. But lots of us cannot run randomized experiments for all the questions that need answering, so we need to figure out how to use observational data to recover causal effects from such data. The critical condition that enables the identification of causal effects from observational data is conditional ignorability. In words, it needs to be true that within subgroups of people defined by certain values of their baseline covariates, treatment is assigned at random. That is, we're taking messy observational data, we slice and cut them until we've broken it into a bunch of little randomized experiments, and those we know how to analyze. So a lot hinges on this on conditional ignorability. How do we justify it? Turns out it's hard. Conditional ignorability is an assumption that can only be justified with respect to your assumptions about the data generating process. So then we moved on to module number 2 and asked, how can we efficiently notate the causal assumptions that allow us to defend the assumption of conditional ignorability? So we use DAGs to do that. DAGs are little pictures of how the world works. They're graphical representations of the qualitative causal structure of the data generating process. Good. After we'd done that, we said, fine, so now we've fully notated our beliefs about the data generating process. What does that imply about data? In other words, if I believe that I know how the world works, what kind of associations would have to be observable in data if I was actually right in my beliefs? So, before the break, we asserted that all you need to know is 3 elementary causal structures. These structures are identified on this slide. 2 variables A and B will be associated if one causes the other in the causal DAG. They'll also be associated if they share a common cause, and they'll be associated if we condition on their common effect. These are the 3 rules of association. Yes, please.
Ask the symbol you use, this upside down pi. How should that be read?
Whoops, I switched notation on you. That's also statistical independence. Sometimes I just use the normal orthogonality sign. With the right typesetting program, it's this upside down pi that's used to denote statistical independence. Okay, now if you're interested in the causal effect of A and B, there are 3 mistakes we could make. We could over-control, that is, we could control on a variable that sits on the causal pathway. If we control for that, we're blocking the flow of association. Second, if we're interested in the causal effect of A on B, we had better control for all the common causes of A and B. Why? Well, these common causes induce an association between A and B, even if A does not cause B. So we want to control for these common causes. If we don't, that's confounding bias. Third, if we're interested in the causal effect of A and B, it's a mistake to control for a common effect of A and B, because that would induce endogenous selection bias. So 3 sources of association map onto 3 problems, the 3 structural sources of bias and causal inference. And, well, what's left for us? What's left for us is to put all of these things together in a concise way and giving it a name. Judea Pearl has done that and has given it the name D-separation in 1988. So here's how this works. It turns out that all DAGs can be constructed from 3 elements: causal chains, forks, and inverted forks. That's it. These are the primitives of graphs. Now, since we understand the associational implications of these 3 building blocks, we just have to put them together artfully to understand the associational implications in DAGs of arbitrary complexity. The D-separation concept does that. So here's the basic logic. Okay, so first sketch the logic, then I'll get more concrete, then you'll get a formal definition. So the logic of connecting the causal assumptions to the associations produced in data in model that conform to your assumptions goes like this. First, kind of as an axiom, we say that causal effects give rise to observable associations. All associations are transmitted along paths, but not all paths transmit associations. Well, what paths transmit associations? Oh, open paths. Open paths transmit associations, and closed paths do not transmit associations. So how do you know if a path is open or closed? D-separation. Pearl's D-separation criterion summarizes our 3 rules of association, and you can use that to unambiguously determine whether or not a path is open or closed, if you perfectly stratify or not, perfectly condition or not, on certain sets of variables. So, what we need to do is figure out whether a path transmits or does not transmit association, whether or not a path is open or closed. Let's do this first without conditioning on anything. D-separation is straightforward when you don't condition on anything. That is, now we're essentially looking at marginal associations and marginal independence. Rule number 1. If you do not condition on any variable, a path between 2 variables is open if it does not contain a collider variable. Again, a path is open if it doesn't contain a collider. Second, again, if you do not condition on anything, then the path is closed if the path does contain a collider variable. So, the presence of a collider marginally closes the path. The absence of a collider opens the path. So I'm just going to assert these rules now and then I'll justify them. Now, you can also use D-separation to determine whether a path is open or closed if you actually condition on something. And the key point here is that whether a path is open or not depends on what you do with the colliders and the non-colliders. Because conditioning or not conditioning on colliders and non-colliders has the exact opposite effect. So here are two blocking rules or closing rules. First, conditioning on any non-collider blocks a path. Not conditioning on a collider also blocks the path. So we have to pay attention to where the no's and nots are here, right? So conditioning on a non-collider blocks the path, and not conditioning on a collider blocks the path. The opening rule is just the converse of this. Not conditioning on any non-colliders and conditioning on all colliders opens the path. Okay. Now here's the formal glory. So a path containing a sequence of edges A, M, B is said to be deseparated or blocked or closed by a conditioning set of variables M if and only if the following is true. It's the path is blocked if the path contains a collider, contains a non-collider M that's been conditioned on. So here, our AMB sequence could contain a non-collider under two scenarios. M could be an intermediate variable, and conditioning on an intermediate blocks the flow of association. Second, our non-collider could be a common cause of A and B. Well, not conditioning on that common cause keeps the path open. Second, a path containing the sequence A and B is deseparated if the path contains a collider and neither the collider nor any of its descendants have been conditioned on. So here, this statement is the exact same of what I've said before, and I want to just show you how this is really just a concise way of putting our three rules of association together. Remember here, so here the first rule says you block the flow of association if you control for a non-collider. Well, a non-collider is either a mediator or a common cause. And intuitively, if you condition on a mediator, you block the flow of association. Also, if you condition on a confounder, it gets rid of the spurious association. And our third rule is that, well, the path is blocked if it contains a collider, and you do not condition on the collider. All right. So that's how you close a path. Now, a path is said to be deconnected or open or unblocked if and only if it's not deseparated. So this will take some practice, and that's why we're here. I'll give you some practice with this. But the key thing to note is that it depends on whether or not you condition on a variable and whether or not that variable is a collider or a non-collider. If you know these three elementary rules of association, you are set. So I'll go back to the conditioning rules. Conditioning on any non-collider blocks the path. Not conditioning on a collider also blocks the path. And not conditioning on any non-colliders and conditioning on all colliders opens the path. Three rules, that's it. And now we're going to, now we have to link this to association. So the formal definition of deseparation is just a property of a graph, right? Laura, yeah. Mm-hmm.
and
Connected is open.
not separated.
Is connected is open.
I guess I just,
Is the
so
opposite, yeah,
it
yeah,
just open goes with,
Use whichever one. So, and these are just the terms that are
okay,
used.
okay.
Yeah.
That's fine.
Okay, so note here that the deseparation criterion just establishes a property of a given graph, or rather a path in a given graph. The deseparation criterion itself doesn't say anything about association. So now we need a theorem that's itself resting on other assumptions that links deseparation to data that were generated by the graph. And so this is just two low-hanging technical assumptions. I'm not going to go into that. But basically, Verma and Pearl in '88 proved that link for causal DAGs. So if you have a graph that contains all common causes and is true, then we can link deseparation to association. And we say that two variables that are deseparated along all paths are statistically independent. Conversely, two variables that are deconnected along at least one path may be associated. Okay. Deseparation is a property of a path. Association is a property of a pair of variables. Two variables that are deseparated along all paths are independent. Two variables that are deconnected along at least one path may be associated. And because this is such oratorious fun, we're going to do a bunch of examples now. And I want us to we'll probably spend 20 minutes on this. But now it really bites me that I don't have a whiteboard here. So if you'll just give me a second, I'm just quickly gonna draw something up in Excel here to make it so you don't have to, take down notation. All right, can you see this? So let's see. So we have variable z1, we have variable z2, we have variable z3. Is this, can you see the z's from the back? You cannot. Okay, I'll make it bigger. How do you make stuff bigger? Here. Yeah. No, actually, don't save here. I'm sorry, thought I'd have a whiteboard. I was mistaken. Okay. Does this align? This roughly aligns. Okay, so we have Z1, Z2, and Z3. The question is, are X and Y independent? Remember, independence results from deseparation along all paths. And now I want to go with you through a bunch of scenarios where we do or do not control for Z1, Z2, Z3, and ask, are X and Y associated or not? So suppose Z1, Z2, and Z3 are binary, and so, stratification is easy. Clearly, we now have to analyze 8 different scenarios. We could condition on nothing. we could just condition on x, just condition on z1, just on z2, just on z3, z1 and z2, z1 and z3, z2 and z3, and 1, 2, 3. Did I forget something? 1, 2, 3, 4, 5, 6, 7, 8. I did not. Okay, good. So we have 8 scenarios here of conditioning or not conditioning on these various variables. Good, so now we'll go through them one by one. Just to practice, and this is example number 1. Whoops, no. Okay. All right, first scenario. If you don't condition on any of the z's, are x and y independent? Well, for that, we first need to look what paths connect x and y. There's only one. And we remember that a path is d-separated if it contains a collider. Does it contain a collider? Yeah! Z1 is a collider on the path from x to y. So not conditioning on Z1 closes this path, since it's the only path that makes x and y independent. Yes! Next scenario. What if you condition on Z1? Does that make x and y associated or independent? So this is going to be just application of these d-separation rules. Nothing else. We'll do this for 20 minutes. Everybody has the opportunity to speak. I encourage you to speak early because the questions won't get easier. Again, we're conditioning on Z1.
It's the only collider, so if you condition on it, then it's open.
Great. Okay. The rule was that if you condition on all colliders and no non-colliders, then the path is open. This is true in this case. Z1 is the only collider we condition on it. Z1 and Z2 and Z3 are non-colliders and we don't condition on them. Great. So that means, are x and y associated or independent? Associated, right, so they're non-independent. Let me say the same thing in a different manner now. Let's see, do I have, here's my fancy electronic pointer, but now I'm standing in the way of half of you, right? Sorry about this. Okay, so Z1 is a collider. Conditioning on the collider induces an association between x and Z2. Because Z2 is a non-collider, the association keeps flowing to Z3. Z3 is a non-collider, so it keeps flowing to y. Thus, conditioning on Z1 induces an association between x and y. Next scenario. What if we just condition on Z2? Somebody else, please.
The collider is causing it to be blocked.
Say that again. What about us?
So we're not controlling for Z1, so the collider is blocking it again.
That's right.
Even for anyone where Z1 isn't marked.
Correct. So as soon as you condition, as soon as you don't condition on any collider, the path is blocked. So in your name? Julian. As Julian said, as long as we don't condition for Z1, x and y are independent. Okay, here we go. Great.
And Z2 and Z3 are not colliders, so conditioning on them immediately breaks the rule.
Correct.
So those are all.
Good. Well, you guys are fast. This is very good because this is good. Let's analyze scenario 5 though, okay, and slightly more slowly. What if we condition on Z1 and Z2? Okay, one by one. Z1 is a collider. Conditioning on Z1 induces an association between X and Z2. Now, because Z2 is a non-collider, conditioning on Z2 blocks the flow of association. Thus, the association goes from X to Z2, and that's where it stops. Okay. So in this case, 2,
I have a quick question.
please.
Can you remind us the definition of a collider?
Yes. A collider is a variable on the path in which two arrows collide. So here in Z1, right, on the path from X to Y, Z1 is a collider because the two arrows on this path that go into Z1 collide in Z1. Right? It's just these two arrowheads go against each other. That's a collider. Is this everybody okay on this definition? Because this is, right, remember I said, forgetting the exact definition of the collider is the number one source of problems in some of the examples. These are the examples. Just wait. Okay. Now, what about if we condition for Z1 and Z3? It's the same story, really. Z1 is a collider. Conditioning on the collider opens the path from X to Z1 to Z2. We don't condition on Z2, so the association flows to Z3. But Z3 is a non-collider that we do condition on, so association is blocked again. Okay, so here we have an interesting case, right? Oh, no, sorry. And then lastly, if you condition on everything, well, as somebody has said already, as soon as you condition on a single non-collider, the path is blocked. And Z2 and Z3 are non-colliders. Great. So this is a cool kind of scenario, right? So we have these two variables, X and Y, and there's only one way to make them associated, but 7 ways to make them independent. We will use this flexibility later, because sometimes you want to close paths, and it's nice to know that there are often many ways to close a path. Please.
You're looking at simply whether X and Y are dependent.
Correct.
Does it add anything, or is it useful to consider the degree to which, so in some cases you
Mm-hmm.
can get as far as Z2, others you can get as far as Z3?
Yeah, that can be used. I thought you're just, yes, it is often.
I'm just
Sorry, there are two questions. First, for any given path, do we just need to know if it's open or closed? Yes. Now, often you'll have multiple paths, so you need to do this exercise for each and every one of them. And we'll do that in a second. That's one part. The other question is, are there degrees of closing? Yeah, in practice there are. But for this workshop, we're acting like we only care about independent versus non-independent. And of course, in empirical bias analysis, you don't just care whether there is bias, you care about whether the bias actually matters. But that's then a quantitative exercise, which needs additional tools. Thank you for the question. Next scenario. So here, guys, I'm looking at the first two graphs. And the first graph, I'm shocked and I apologize. I gave you the wrong graph to analyze. I forgot that there's a common cause between Z1 and Z3. It's unobserved. Now we know that deseparation only works in causal graphs. So I'm sorry, we analyzed the wrong graph. We have to analyze graph number 2 now. Now, this graph is different. We'll have to start from scratch. Again, I will ask, are x and y associated or independent if my data were generated by a causal model with this structure. So we know, again, that two variables, x and y, are independent if they're deseparated along all paths. Hence, first we have to enumerate all the paths between x and y. Somebody want to tell me the paths? Just give me the first. What's the first path between x and y? Any path. Okay, so the one that goes straight through, right? X, z1, z2, z3, y. So another path?
Through the unknown.
That's right, through this mountain there. X, z1, u, z3, y. Is there a third path? No, there is not. Okay, good. So in order to determine whether x and y are independent, we have to analyze whether our various conditioning sets render both of these paths deseparated.
So it's a strict intersection, right?
Yeah.
Okay.
So what if we don't condition on anything? We already know that if you don't condition on anything, then the path that goes straight through is closed. What about the path that goes through you? Yeah, why?
Because there's a collider between u and x at z1.
That's right. Z1 is a collider on both paths. Therefore, not conditioning on Z1 makes x and y independent. Very good. So we don't condition on Z1, we don't condition on Z1, we don't condition on Z1. Very good. If you do not, so if there's an unconditioned collider, the path is closed. That's what we've used here. Randall. Did you have a question?
Yeah, what happens if we condition on u?
It's unobserved, so we can't condition on it.
All right, so
This
what
exercise
about
turns on that.
You would need 16 cases instead of 8 because we would
Yes.
depend on the.
Okay, next case. What if you condition just on Z1? I want you to really practice this. So somebody who's not said anything and you know who you are, you want to give it a try. It's okay if you can't do it, because then I know what I need to explain again. Yes? If I just condition on Z1, so what do other people think?
It's closed. Because it has to work for all paths, right?
No. No. So Z1 is a collider on both paths.
Right, but Z3, though, is a collider on path 2.
Is it?
No? The unobserved doesn't count?
So
Oh,
the,
there's no Z2 there. So there's no Z2 there. Yeah,
the, the second path,
Right.
Z1 is the only collider on both paths.
Right.
Let me roll this out. So some of you might see that there are two arrowheads going into Z3. Yeah, that's true. But there is no path from X to Y that goes U, Z3, Z2. So that fact is irrelevant. Z3 is a non-collider on both paths. Okay. Now if we condition on Z1, it's the only collider on the bottom path, so that opens the bottom path. Z1's also a non-collider, a collider on the path through U. It's the only collider on that path, hence conditioning on it opens it. Cool. So that means if we condition just on Z1, X and Y are deconnected via both paths. What now if we condition on Z1 and Z2? Look at this for a minute. Please.
Are they dependent because there's a path, even though you're conditioning on both Z1 and Z2, you have a path through U to get.
Aha. That is the correct solution. Now let's slowly elaborate how you arrived at this solution. Do you want to give it a shot? Do you want to tell us how you arrived there?
Oh, no, thank you.
Okay, again, X and Y are going to be independent if they're deseparated along all paths. By contrast, X and Y are going to be associated if there's at least one open path. Now let's analyze both paths when we condition on Z1 and Z2. First, let's look at the bottom path. On the bottom path, Z1 is a collider, so X becomes associated with Z2. But Z2 is a non-collider, and conditioning on a non-collider blocks the flow of association. Therefore, the bottom path is closed. What about the top path? On the top path, Z1 is a collider. So conditioning on Z1 induces an association between X and U. Now we additionally condition on Z2. But Z2 is not on this path, so it doesn't do anything. So we have an association between X and U. It travels on to Z3. It travels on to Y. We have one closed and one open path. But the one open path is enough to induce an association. Please.
Could you perhaps think of an example off the top of your head of when we would have an unobserved variable that's skipping one of our other variables like this?
Now I have to come up with a story involving 4 variables. I don't have that at my fingertips, I'm afraid. Okay, what if you condition on Z1 and Z3? Again, take a minute, and I want everybody to try to solve this for a minute, and then we'll do it. Pardon me?
Both paths are blocked.
You're sorry, you give me the solution. Let's have a show of hands. Do you think that conditional on Z1 and Z3, X and Y are independent because both paths are blocked? And who thinks they're open? The force of democracy, right? There are some undecideds, but that's okay. Yes, you're absolutely right. Do you want to explain why?
Because both Z1 and Z3 are colliders. So what happens is the first path, which is the bottom path, is blocked when Z1 is blocked, is conditioned on, and the second path would be blocked when Z3 is conditioned on.
That's not. So your answer is correct, but the solution is not. Yes, please.
So Z1 is the collider in this case, and Z1 is blocked.
Z1 is conditioned on, so
Yeah,
that.
Sorry, Z1 is conditioned on, but we have another alternate path open to U, and Z3 is blocked, which is a non-collider, but it is going to stop at that.
Okay.
So X and Y are going to be.
So I see where you want to go, but we've got to be careful not to confuse blocking with conditioning.
Excuse me, sorry.
Whether or not conditioning blocks or opens a path depends on whether the variables are collider or non-collider. Let's have a third attempt here. Yes, please.
So Z1 is a collider, so when you condition on that, you're opening both of the paths.
Mhm.
Z3 is a non-collider on both paths, so it blocks both of them.
Triumph! Okay, fantastic. I'll say that, I'll repeat that verbatim if I can. Z1 is a collider on both paths. Conditioning on a collider opens the path. So conditioning on Z1 opens both paths. So association flows and flows until it reaches Z3. Z3 is a non-collider on both paths. conditioning on a non-collider blocks the path. Hence, conditioning on Z3 closes both paths, rendering X and Y independent. Again? Are you cool? You got to tell me, like, this is the moment where we practice everything we've learned so far. And if you're like, let's move on, oh yes, we will.
So, knowing that Z3 is a non-collider and every path goes to Y,
Mm-hmm.
the only really relevant piece of information, once you know Z3 is
Mhm.
conditioned on, is that information.
Indeed, that is the case. Yes, I'm glad you see that. That's right. Conditioning on Z3 is sufficient to close all paths. So if we know that Z3 is conditioned on, we know the X and Y are independent. Yep. Exactly, which gets us to our last scenario. You condition on all three Z's. Sorry, your name? Thomas. Thomas pointing out Z3 is a non-collider on both paths. Condition on it, and you're done. So we're done. Okay. Now, I'm going to play a similar trick on you. I'm like, I'm so sorry, wrong dag. I forgot to tell you two other facts. First, there's another unobserved variable between X and Z1. And there's a direct causal effect of Z1 on Y. This is a different causal model with different assumptions, far fewer exclusion restrictions. So we have to reanalyze the question of whether X and Y are marginally or conditionally independent. Example number 3. Okay. So, first I want you to enumerate paths. Count quietly, okay? I know some of you, for some of you, this is an exercise you've already done. Others do this for the first time, so give everybody a chance to do this. How many paths are there between X and Y overall? Just count them. So now we'll do a little show of hands because it's after lunch and we need to exercise. So I'm going to ask, can you see at least X paths? And you're going to be, yes! And you keep your hand up until I give you too many. So do you see at least one path? Do you see at least 2 paths? At least 3? At least 4? At least 5? At least 6? At least 7? Oh man, you've all taken graph courses. Super, okay. Sorry? So there's exactly 6 paths here. The way to enumerate them is note that every path clearly has to go through Z1. So there are 2 ways to get from X to Z1, and there are 3 ways to get from Z1 to Y. So twice 3, 6 paths. Turns out to be a non-trivial enumeration exercise, actually, if the DAGs get more complicated. But computers can do it. So let's actually enumerate these paths so we can keep them in our head. And you might want to actually write these out because things get messy. So we'll go bottom to top. The first path goes X to Z1 through the belly to Y. So that's the belly path. Then we have the path that goes straight through. Then we have the path that goes up and through the belly. Then we have the path that goes straight and up. And then we have the camel path, up and up. 6. 6 paths. And in order to determine whether x and y are independent or not, we have to determine whether any one of these paths is open or closed.
Well, anyone open or all closed.
Correct. So, and at this point you're like, geez, man, this is why this course goes to 5:30. Right on. But if you master this one, the rest is going to be mere application. You know, deseparation is the heart of working with graphs. And we want practice. So, if you don't condition on anything, are x and y deseparated along all paths? Or is there at least one open path? Put your hand up if you find your first open path. 5 people have found an open path. Tip, there is an open path. Everybody find it. Hands up if you see 2 open paths. No, don't turn this hand raising into grooming, because you're right, there are 2 open paths. Well, let's find them. Okay, so give me one open path. Anybody? Who? Is it in the corner? Correct. This path is open because on this path, Z1 is a non-collider. Everybody. The path that goes straight in through the belly, on this path, Z1 is a non-collider. Is there another open path? Yes, Thomas. Very good. X, U1, Z1, Y. So the path that goes up and belly is open. Because on this path, too, Z1 is a non-collider. Arrow in, peaceful departure.
XU1, Z1, U2, Z3, Y.
Is that open?
Who's a collider?
What?
The area. Yeah.
Z1 is a collider on that path. That's right, so that's not open.
Yeah.
Yeah, so there are exactly 2 open paths here. Of course, the difficulty of seeing that results from the fact that there are so many arrows going to Z1, right? So is Z1 a collider on a specific path or not? You really have to squint. The second problem that I've encountered when I give this example to folks is that lots of people intuitively want to start paths with an arrow out from X. But here you have a path that starts with an arrow into X. Don't neglect those. They're paths too. Okay, good. So in sum, we've established that if you don't condition on anything, then there are 2 open paths between X and Y. These 2 open paths are the paths that go through Z1, where Z1 is a non-collider. On the 4 other paths, Z1 is a collider, and hence they're blocked. So marginally, X and Y are now dependent. Okay, what if you do condition on Z1 and only Z1? Randall.
Anywhere you had a no stays no.
I should not call on the mathematicians here. No.
Isn't the path I said?
No. Sorry, yes. Anytime it's associated, it stays associated. That's right.
Because you haven't
Be-
taken away any paths.
Because I haven't taken away anything. That's correct. Sorry, I switched this in my mind. Yes, exactly.
The same thing for number 5.
Nonetheless, let's justify this just, on the merit of this graph alone. For x and I'll just
Well, I was just
finish
gonna
this.
say the path that I said that was wrong for the first one would be right for the second one because the only
Correct.
collider was Z1.
Yeah, so I'll enumerate the open paths now. So we're just conditioning on Z1. This will open any path on which Z1 is the only collider. These paths are the one that goes straight through, the one through U2, the one through the camel, and the one that goes up and straight. So conditioning on Z1 opens 4 paths. The other 2 paths are closed because on these other 2 paths Z1 is a non-collider. Okay, so conditional on Z1, X and Y are not independent. Whoops, we already had this. So now what if you just condition on Z2? Are they independent or associated? They're associated. That's right, because these 2 paths on which Z1 is not a collider stay open. I'll show you these paths again. So you condition on Z2. What paths remain open? Well, the one straight and through the belly, and the one up and through the belly are open. It's always okay to say, hey, man, just do this again, okay? Yeah, Laura.
I have it on X, Z1, U2, Z3, Y. Is that one also?
Which one?
X, Z1, U2, Z3, Y?
That one is closed if you only condition on Z2,
Okay.
because you did not condition on Z1.
Okay.
And
Okay.
Z1 is a collider on
Z1
this
is a
path.
collider on that path. Okay, got it.
That's right. Very
That's
good.
right, 'cause the error, okay.
Mm-hmm. Cool. What if we condition just on Z3? Are there any open paths if we condition on Z3? Well, okay. Good. The belly ones. That's right. The one that goes straight through the belly and up through the belly. Adding these errors clearly made a difference, right? What if you condition on Z1 and Z2? Are there any open paths? There's a harder one. Let's take a minute. Everybody try. Z1 and Z2. Okay, so you condition on Z1 and Z2. Hands up if you see at least one open path. That's great. Okay, super. Which one is open?
One that goes to Z1 and then up.
The one that goes Z1 and up through U2 to Z3 to Y. Correct. That one is open. Is there another open path? There is, but which one? So is there another open path if you condition on Z1 and Z2?
But if you go up through U1, you go up through U1 and then up.
Right, the camel. U1 to Z1, you hit the collider, you go to U2, Z3, Y. Yeah, so there are open paths, so they're non-independent. Man. What if you condition just on Z3? Any open paths? Yeah, the ones that go through the belly. What if you condition on Z2 and Z?
It's not just Z3, it's Z1 and Z3. So if you
Sorry, I didn't
so
see
if you
that.
go through the
Right.
belly, then that means Z1 isn't a collider.
Never
it's
mind.
a collision.
Good. Z1 and Z3. Sorry, I was in the wrong one. So Z1 and Z3. Everybody look at this. Yeah.
I have a question on number 5.
Okay.
Can you go through X V1 and then down below to
Aha. So if we condition just on Z1,
You said line 5, right?
on line 5, yeah.
Sorry.
so which
your-
one?
your
Oh,
five.
this
Yeah,
year,
yeah,
this
yeah.
year. So you condition on Z1 and Z2. Okay. And now what was the question?
Weren't there 3 paths? Can you also go through X Z1 and then down below to Y?
No, because on that path, Z1 is a non-collider.
Okay.
And conditioning on a non-collider blocks the path.
6 is just
Okay.
a bad recipe because depending on whether you want Z1 to be a collider,
Mm-hmm.
so like if you try to go through the belly,
Mm-hmm.
Z1 isn't a collider, so you're
Mhm.
not allowed to use the belly.
Mm-hmm.
And then if you avoid the belly, you have to go through Z3,
Mhm.
but Z3 is always a non-collider, so you would have to.
Very good.
Yeah, you can't condition.
Very good. I'll repeat this. So finally, we've made X and Y conditionally independent of each other. There are 2 sets of paths. The first set of paths go through the belly. On these paths, Z1 is a non-collider, and conditioning on the non-collider blocks these paths. Good. Now there's a second set of paths. They don't go through the belly, so they have to go through Z3. Z3 is a non-collider on all of these paths. Therefore, conditioning on Z3 blocks all the remaining paths. Hence, they're independent. What if you condition on Z2 and Z3? Anybody?
And you can still go through Z1.
That's right. So if you condition on Z2 and Z3, the belly paths are still open. So non-independent. What if you condition on everything? Well, we already know that if you condition on Z1 and Z3, they're closed. Z2 is a non-collider, so that doesn't change anything. Good. Yes, good. Okay. You did well. You did 10 minutes better than I think I could reasonably assume, based on the information that there might be high schoolers in this audience, but there clearly are not. So now let's compare these. Okay. So what we've done is we've applied deseparation to 3 causally different models. These models have an interesting structure in that they're nested within each other. The model, which one is the model with the most assumptions? 1, 2, 3, 1, right? 1 has the most assumptions because it has the fewest arrows. So that's the most restricted model. Now you might look at this and say, oh, this is this is a simple model, but it's not. It's making all sorts of assumptions. We get to number 2 by relaxing the assumption that there's no U. And we get to number 3 by relaxing the assumption that there's no U1 and no belly path. So as we go from top to bottom, we successively relax assumptions. We never add assumptions, we just take them away. Now note what effect that has on independencies. In the first really restrictive model with the many assumptions, it's easy to get independence. But as you relax assumptions, your independencies fall away. So in the third model, you have very few independencies left. This is a general feature. Relaxing assumptions removes independencies. It never adds independencies. And inasmuch as we need independencies and exclusions to do any work, it's clear that we need assumptions. Okay. Well done, everybody. Questions?
Does the D separation stand for dependent?
For directional. D-separation is directional separation. Ask me not why. Thank you.
I think it helps bring to answer Laura's question of what connected block is.
Yeah.
Does it? Okay.
Well, I had it as blocked. Open allows association.
Mm-hmm.
Block.
Yeah.
Okay. That's how I.
You separate the pipeline or something. Terminology. Michael?
Yeah, I appreciated you zooming out there at the end to provide the big picture because I was getting lost in the forest a bit. Could you take it a little further? You said, hey, as we add, as we relax assumptions, thank you, then we lose independencies.
Yes.
And that's bad.
That's bad for reasons we'll see soon why, because eventually we'll want to do identification analysis. And we'll need them for that. I mean, so another way, so here's another reason. If you want to test your data, what we test are independencies. And so if you lose independencies, you lose things where you can test your model. You know what, with this audience, I'm massively surprised that I didn't get the following question. The question would go something like this. Gee, thanks, Felix, but isn't there software? And there is. And there is. There are various R scripts that do that. There's a free online interface called Dagity that does this for you. But I'm not bothering to show you these things because you can all use Google. And I think it's inimical to learning to let the machines do the work right away. I firmly believe that two things are absolutely necessary to become a confident user of DAGs. First, you have to translate a bunch of prose stories or expert opinions into graphical models. Second, you need to analyze a bunch of DAGs in order to get a feeling for what structures are potentially problematic. If you do that for a bit, for example, with my three favorite examples here, you will develop a feel for it, right? So for example, if you see a variable like z1 with tons of arrows into it, you'll immediately go, oh, wait, this variable is likely a collider on some paths and not on others. Better be careful. Okay, so I strongly recommend practice. Please.
What about U1 and U2 being unobserved? Could you remind me, does that mean that we know what the variable is and we just didn't measure it, or we don't know what that variable is?
Drawing U1 here means that I'm not willing to exclude the possibility that there's some unmeasured cause that causes X in Z1. Ideally, I'll be able to tell you a story about what this is, because otherwise I'd just be saying, or it could be. But perhaps you're in a situation where it is of paramount importance for the survival of your patient population that you don't get this part wrong. Well, in that case, better safe than sorry.
So
Laura.
in that software, does it tell you all the possible association structures
Yep.
that would be consistent?
Mm-hmm. Yeah, it does. So let's continue doing this by hand just a little bit and go and let's ask, why on earth would we do this? Oh, sorry, another question, Julian, right?
Is there degrees of association? You have a bunch of open
Not under conditions that we've used so far. If you want to know the strength of an association, at a minimum you need to sign and size these arrows. That's information we've not yet introduced. And it turns out to be a non-trivial task. In a nonlinear model, in a linear and homogeneous model, each arrow can be described by just one path parameter. But if you have effect heterogeneity, things are not so clear anymore.
When I look at these three, I see kind of a parallel to simple linear regression, the first one, and then levels of multiple regression.
No, not necessarily. No, in both, if I'm interested in the causal effect of X and Y, then the most complicated. So then in each of these three models, I could run the regression of Y on X and all the Z's, or any combination of the Z's.
It's more in terms of the assumptions being made and the apparent simplicity of the model.
So we will get to regression in about an hour and a half, where I'll say, suppose you estimate a given regression. How does the interpretation of the coefficients change if your assumption about the underlying data generating mechanism changes? That's what we're not there yet.
Yeah, I was looking for whether there's and maybe that's what we're saying is that if you allow the lack of assumptions in the third model, that's not a good thing.
Well, it depends. We will revisit this, right? So it's always a question of good thing for what? A good thing for the identification, non-identification of certain effects. So first we have to define what effect we're interested in, and then we have to see if we could recover that from any one of these three models. And that is, in fact, the goal of the next module.
Would this be a decent opportunity for a bathroom break or no?
We've gone for 75 minutes and it's after lunch. Absolutely it is. Let's start again at 5 to 3, 10 minutes, is that okay? Excellent. Terrific. Well, welcome back. We're in the middle of, no, we're not in the middle actually. We've succeeded now in connecting our causal assumptions about how the world works to data. Because we've now determined, using deseparation, to what extent we should see dependencies or independencies between variables in the data if our assumptions about the data generating process are true. So what do we do with that? I want to just gesture at this because this would merit another hour. But one thing for which that's useful is to derive testable implications of a model. So we've noted a million times now that assumption-free causal inference is impossible. All causal inference is conditional on a model of data generation. Even in a randomized trial, right? The assumption is that we're actually looking at a successful randomized trial. So if our inferences are conditional on the model, doesn't it behoove us to test the model as best possible? Why, yes, it does. And deseparation tells us all the things that need to be true about the data if our model was actually correct. So let's look at this little graph here. This is strongly related to a graph we've already analyzed. And here in a paper of mine, I went to the trouble, before there was software, to write out all the marginal and conditional dependencies and independencies. And there are so many that I had to invent shorthand, and I even made mistakes. But as you can see, there's a ton here. Now, not all of the statements that this graph implies are testable. For example, this graph implies that X and U should be marginally independent because all paths from X to U contain the collider Z1. If you don't condition on Z1, X and U are independent. Well, of course, that doesn't buy you anything because U is unobserved, so you can't test anything about U. But the graph also implies that X and Z2 should be marginally independent. Furthermore, the graph, yes, let that be it. Now, these independence statements involving only observed variables, those you can test. So hence, they are the testable implications of a model. Now, most fields don't test their models at all. They just assume them. You know, they have a conversation with God. God gives them the right model, and then we go forward. I envy that. In some fields, people do test their models, especially fields that have been touched by structural equation modeling at some point in their history. But it's not at all clear how best to test a model. The usual approach to model testing is to just compare one model to another model with a chi-square test. Okay, and if maybe you test rejects the simpler models, you don't reject the more complicated model. But rejecting the simple model doesn't tell you where the simple model was wrong. So a different approach to model testing would be to test out each and every one of these particular local independencies. That'll tell you where exactly the graph went wrong. But of course, you suffer all the usual problems of over-testing. So that's a statistical topic. I'm not really going to deal with it beyond what I've said, except to say that, yeah, this is why we have statistics. And as you all know, working with real data is really, really hard. So no, it's not really clear how best to test a model. But I think we can agree that we should test the model somehow as far as we can, rather than just letting the model fall from the sky. Now, there are limitations to model testing, which are the same as the limitations to statistical learning. Even under ideal conditions, that is an infinite sample size, no measurement error, you can never test all assumptions in the model. Never. Why is that so? Well, recall that in order to work with DAGs for causal inference, you need to have a causal DAG. That is, a DAG that includes all common causes. Clearly, we can never test out the absence of all possible common causes, because there's a bunch of causes that are common causes that are unobserved. And there are probably some common causes that aren't even known to science yet. So how are you going to test something about something that you don't even know exists? Wasserman and Robbins used that intuition to furnish a proof for the necessity of causal assumptions for causal inference. Okay, so that's the first limit to statistical learning. The second is so-called observational equivalence. It's almost always the case that causally distinct models can generate the same observed dependence structure in your data. So suppose that you're given the mother of all data sets, 400 million observations on A and B. Well, let's try to recover the causal model from this amazing data set. No measurement error either, by the way. It's super. It's a great data set. And you find that A and B are associated. So, okay, I guess it could mean that A causes B. It could mean that B causes A, or that A and B share a common cause somewhere. These are distinct models, and depending on what A and B actually represent, it might really matter what model has generated these data. But the simple dependence structure of the data doesn't help you. So now, can we add extra statistical information? That is, can we add information that goes beyond just the joint distribution of the data? Sure, we can, right? We could add temporal information. Perhaps we're told that A happens before B. Ooh, that rules out this model. But we still have these two. So how can we go further? Well, we could make the heroic assumption that we observe all variables in the causal DAG. The assumption that we observe all variables in the causal DAG together with temporal order would get us to AB. But note that we've just moved far beyond statistics. And the assumption that we have all the variables in the causal DAG is itself a causal assumption. So structural learning is a very big area right now, and progress is being made. It's provably impossible to recover a DAG without causal assumption. And generally, even under the assumption that you observe all variables, you will just get a class of observationally equivalent causal models, not usually the only one possible model. And that's too bad, because our identification analysis presupposes that we have the one true model. Now, sometimes we're lucky and we could see if we have a class of 3 possible models that could have generated the data under the assumption that we observe all variables possible, then we could see if our analysis of these 3 possible models yield the same result. If that were so, that'd be great, right? But that's usually not the case. So again, there's an extraordinary burden on knowing where the data come from, on knowing how the world works in causal inference. And the more you know about the process that generated the data, the easier it gets. Okay, now, let's actually do identification. Recall that identification means that we can separate the causal association from the spurious association. So the goal in this section here is to determine whether a causal effect can be non-parametrically identified from observed data that were generated by a specific presumed DAG. And the concepts that we're going to encounter in this section are adjustment, the adjustment and backdoor criteria, the relationship between adjustment and ignorability, and probably the parent criterion. So, what's a graphical identification criterion? A graphical identification criterion is just a set of rules, graphical rules, that determine whether a causal effect is identifiable given observed data generated by the DAG. There are a ton of graphical identification criteria out in the literature. Most of these criteria are sufficient. Sufficient criteria say things like, if this criterion is met, then the model is non-parametrically identifiable. But you should note that if a model fails given sufficient criterion, the model may still be identified via some other criterion. So the question is there a complete criterion that tells us unambiguously whether or not a query is identified given a model? Yes, there is. It's Pearl's do calculus, proved in 1995. The do calculus is a complete identification criterion for the causal effect of interventions in arbitrarily complex DAGs. And the do calculus also just uses 3 rules. Unfortunately, the third rule is, I would classify it as massively counterintuitive. So we're not going to do it in our one-day workshop. Instead, we're going to study arguably the most important sufficient identification criterion in practice, the adjustment criterion, which is a version of the famous backdoor criterion. The adjustment criterion underlies any causal claim derived from regression and matching type estimators.
So the due calculus is like a necessary and sufficient.
Yes.
But
It's complete.
Right,
Mhm.
but it's difficult. The top sufficient criteria you're going to offer, do you have any, like, is it common that it like fails all those top ones and still passes the due calculus? You know what I mean? Like,
I am not aware of an purely substantive paper that has to use the due calculus.
Okay.
I know of plenty of carefully cooked up methodological examples of the type that I've given. It's like, ooh, can I construct a graph without any substance to have certain properties? Yes. But no, the famous sufficient criteria are sufficient for a reason, and the adjustment criterion is the one that almost everybody implicitly uses all the time. There's software for the due calculus too. Okay, R scripts, Daggerty uses it. We're going to study the adjustment criterion because I think it's going to give you really valuable intuition for practice. So here it is. Again, what's identification? The causal effect of T on Y is said to be identified if it's possible to purge all non-causal association from my association such that only the causal association remains. Again, you have an association between treatment and outcome. You want to strip away all the spurious association and retain the causal association, because that's your causal effect. So how does that translate to a DAG? Well, it translates through Ilya Spitzer, Tyler Vanderweels, and Jamie Robbins' adjustment criterion. One way to take this intuitive statement that we want to just get rid of all the spurious stuff and retain the causal stuff is to say, hey, how about we block all non-causal paths and leave all causal paths open? Because that's exactly what we'll do. The total causal effect of T on Y, I'm just reading this now, the total causal effect of T on Y is identifiable if you can condition on or adjust for a set of variables Z that blocks all non-causal paths between treatment and outcome without blocking any causal paths between T and Y. That's the intuition. You're interested in the effect of T on Y, block all non-causal paths, leave the causal paths alone, and you're good. Sure, Michael.
We talked about before how it didn't make sense to condition on an unobserved variable, for example. So do you also kind of impose some restrictions, like, hey, we're not going to bother to look at those ones?
No, we do have to consider the unobserved variables because they might create spurious paths, right? So these would be paths that you can't do anything about then. But I'll give you a bunch of examples. I think this will become clear. So let me just add a little bit of formality here. Say that a set of variables Z, which may be empty, fulfills the adjustment criterion relative to the total causal effect of T and Y if and only if Z blocks all non-causal paths and no element of Z is on a causal path or descends from a variable on the causal path. Again, let's see how this is basically what we've said before. Here we're saying we need to block all non-causal paths. That's clear. Here, no element of Z is on the causal path. It's also clear. Because if you condition on something on the causal path, you block the path. And now here's the is more difficult to justify. You also are not allowed to condition on a variable that descends from a causal path. I'm not sure if we have time to justify that, but this is a necessary ingredient in this criterion. So, what's the difference between all these concepts? Well, they're closely related. We've introduced deseparation, independence, and identification. I'm very fond of this slide. Deseparation is a property of a path. A deseparated path means that no association flows along the path. Independence.
So that's really a property of a path and which things you're conditioning on.
Yes, thank you. Independence is a relation between variables. Two variables are independent if they're deseparated along all paths. And finally, identification is a property of a causal effect. Identification means that treatment and outcome are deseparated along all non-causal paths and deconnected along all causal paths. Right, so you have a clear, it's not quite a hierarchy, but first comes deseparation. From deseparation we can deduce independence, and from deseparation we can deduce identification. And because you're so good at deseparation now, we can do identification relatively quickly by looking at our old friends, these two examples. So the first example here is one that we haven't analyzed yet. So let's start with that. I want to know if the causal effect of x on y is identifiable via adjustment for some set of variables z. So is there any set of variables that will deseparate x and y along the non-causal paths without blocking the causal paths? I'll do that with you for the first one. So the first thing we need to do is we need to, again, enumerate all the paths between x and y. How many paths are there? 1, 2, 3. There's the one straight through, the one through the belly, and the one through the mountain. These are 3 paths. Now we need to decide whether any given path is causal or non-causal. So what are the causal paths from x to y in the first model? Anybody?
There's only one, the belly.
There's, yes? There's only one? Which?
The belly.
The belly, yes. So x to z1 to y is a causal path because the arrows go strictly away from x and strictly toward y. Okay, remember that's the definition of a causal path. Good. The other 2 paths are non-causal. Why are they non-causal? Well, because they force you to engage in time travel. The one that goes straight through is a non-causal path because you go from z1 against the arrow of time to z2. The one through the mountain is non-causal because you go from x to z1 with time and to u against time. So if we want to identify the causal effect of x on y, we need to close these 2 non-causal paths on the top while leaving the causal path on the bottom open. So look at this for a while and see if you can do that. And in that time I'll bring up my Excel thing again. Let's call this example I1. So let's see. What if I don't condition on anything? Does that identify the causal effect of x on y? Julian?
Yes, because
Speak up, please.
since Z1 is not conditioned on, and it's a causal relationship, we can flow right through. The other paths are not non-causal, so having that be a collider, it stops there.
Right. I'll repeat what you said was exactly right. I'll just repeat it for everybody. Let's look at the causal path first. The causal path is open if you don't condition on anything. That's a general property of causal paths, right? Causal paths don't contain colliders, so they're open if you don't condition on anything. That's great. What about the two non-causal paths, though? Well, in these two non-causal paths, Z1 is a collider, and since you don't condition on the collider, the association stops there. Thus, not conditioning on anything closes all non-causal paths and leaves the causal path open. Yeah, you can identify the causal effect by just looking at the bivariate correlation between x and y. The only association that contributes to this correlation is the association flowing along the causal path. Cool. What if you condition on Z1? Is the causal effect identified or not?
That's that again.
Can we identify the causal effect of x on y by conditioning on Z1? I want to give everybody a chance to practice. Anybody? Please.
No, because on the causal path, C1's a non-collider, so if you condition on it, you close that path.
Mhm.
It's a collider on the other two paths, the non-causal paths, so if you condition on it, you open those two.
That's exactly right. What's your name, please?
Lauren.
Thank you, Lauren. So what Lauren said is exactly right. Conditioning on Z1 is like the worst thing you could do. Remember, in order to identify the causal effect of x on y, you need to close all non-causal paths and keep the causal path open. And conditioning on Z1 does the exact opposite. Conditioning on Z1 closes the causal path and it opens the two non-causal paths. The conditional association between x and y given Z1 is entirely spurious. So, don't condition on Z1. Whenever you condition on Z1, you're going to close the causal path of interest. So let's don't. Here, whenever we condition on Z1, the effect of x and y is not identified. Well, okay, I have a different proposal then. How about we condition only on Z2? Can we identify the total causal effect of x and y if we condition on Z2?
I'm going to say no, because it still allows you to go around U.
Does it?
If you condition on Z2,
Mm-mm.
but not on Z1.
Mm-mm.
There's only one way.
See? So so I've tilted my hand here. Conditioning on Z2 alone is okay. But why?
The same reason that leaving them all open is okay, or leaving them all unconditioned, because
That's right.
the collider is equal.
Okay, so we have one causal path. Conditioning on Z2 does not block that causal path. Whew. We have two non-causal paths. They're both closed if we don't condition on Z1. Now, additionally conditioning on Z2, whatever, who cares? It doesn't matter. The non-causal path through Z2 was blocked already, and it stays blocked after conditioning on Z2. So yeah, it's okay. You can condition on Z2.
So I guess
Julian.
experiment design, it might be better to control for some variable. It seems that at this point,
Yes.
the simplest solution would just leave it open.
Well, no. The path through Z2 is blocked anyway. It's closed anyway. But the question is, do you want to condition on Z2? So yes, in experimental design, you probably would want to condition on it because efficiency. But we're not dealing with efficiency here. We're just dealing with identification. I'll say something about why you might unnecessarily want to condition on variables. I'll come back to this. This is a good point. Okay, so what if we condition just on Z3? Somebody other than Lauren who knows the answer.
Isn't that the same situation as when you condition on Z2?
Bingo. And what is that situation?
Z1 is still the collider. So the path from X to Z1 to Y.
Mm-hmm. That's right. So we now condition just on Z3. And we need to ask, does that leave the causal path open? Yes, Z3 is not implicated in the causal path. Are the non-causal paths, these two, still closed? Absolutely. They're closed because you're not conditioning on Z1. Whether or not you condition on Z3 is irrelevant. Very good. So identified. Leaves us with the question what would happen if we conditioned on Z2 and Z3? Thomas?
Same argument.
Same argument. Thank you. Good. Everybody see that? Very good. Okay. So that's pretty good, right? So here we have, if we want to identify the causal effect of X on Y, we have various ways in which we could accomplish that. We could just not condition on anything. We could just condition on Z2, just on Z3, or on Z2 and Z3. Non-parametrically, these four different strategies for identifying the causal effect are identical. By which I mean any non-parametric estimator will be similarly consistent. So then Julian broached the question of why would I ever want to control for any variables if I don't have to control for any variables? Well, we don't have to control for any variables here for identification. But in a real data exercise, we still have to worry about efficiency, right? How precise is our estimate? And there the general rule is that you want to control for causes of the outcome because causes of the outcome suck up variation in the outcome, and the less variation you have in the outcome, the more efficient your estimate. So, yeah, you want to control for the causes of the outcome, but be careful. You can only control for causes of the outcome that don't open non-causal paths or open close causal paths. That's why in experimental design, the usual recommendation is that you should only ever control for pre-treatment variables. Pre-treatment variables clearly cannot be on a causal path. Cool. Next model. Here I'm reintroducing U1. What happens to identification? So again, the adjustment criterion tells us, so let's call this model 2, that the causal effect of x and y is non-parametrically identifiable if you can block all non-causal paths without blocking any causal paths. In this graph here, we have 6 paths. How many of them are causal and how many of them are non-causal? Partial answers accepted. There's just one causal path. The causal path is x to z1 to y. Does anybody want to check a second path? Okay, good. So that's the only causal path. That means we have 5 non-causal paths to worry about. Well, let's see. If we don't condition on anything, is the causal effect of x and y identified? So who thinks that not conditioning on anything identifies the causal effect of x and y? Okay. Who thinks that it doesn't? And the rest is unsure. Okay. Yeah, so suddenly, right, we introduce one more variable with 2 more errors and suddenly it gets a lot more complicated. Let's see, who wants to try their answer? Who wants to explain it? And like patiently for everybody. Yes, and sorry, I don't know your name. Mhm.
If you don't condition on Z1, then the causal one stays open.
Mm-hmm.
And all the other ones are closed regardless of what you do with Z2.
So the first statement is correct. If you don't condition on Z1, the causal path is open. But, sure, yes, you, please.
Yeah, there's still a remaining non-causal path, x, u1, z1.
That's right. So everybody look at this path. X, U1, Z1, Y. This is a non-causal path because it goes against the direction of the arrow here. It's also an open path because Z1 is not a collider on this path. We could close this path, but only by conditioning on Z1. And if you condition on Z1, then you're closing the causal path. In sum, if you don't condition on Z1, it's not identified. If you do condition on Z1, it's not identified. So here you have a causal model where the causal effect of x on y is not non-parametrically identifiable. That's too bad. This happens a lot. Yeah, so we can, we've been able to draw the DAG. We're confident that we have the data generating mechanism. We've measured what we measure. We've formulated a coherent causal question, and we've concluded that we cannot answer it in the system. So I have a question for you. If you compare these 2 models, what kind of studies are we looking at? Do you have a name for a study that would generate the first graph? What kind of study generates, where X is treatment, generates a graph like this? Might this be a randomized experiment? Why, yes, it is. only in a randomized experiment. Laura, yeah?
I just wondered if it could be like dropouts or something, like,
Drop.
or no.
Mm,
If this was
I was
like
looking
this
for
was-
experiment.
What?
I was looking for experiment.
Okay. Okay.
So,
They-
sorry. So here, X is the treatment. There is no systematic input into X. X varies by pure random chance. When is that ever the case? In a randomized experiment. So once you see that, perhaps it's no longer quite so surprising that you don't have to control for anything in order to identify the effect of X on Y. You don't have to control for anything because it's a randomized experiment. And you know, like in any randomized experiment, there are all sorts of things that happen downstream. But who cares? Randomization itself gives you ignorability. You know, in a randomized experiment, there are no open, non-causal paths. By contrast, what's this kind of graph representative of? A lot of observational studies. Here in this study, treatment choices are confounded by some unobservable stuff. Unobservable stuff that also affects other things on the causal pathway. So you can think of U1 as the killer confounder. U1 causes treatment and indirectly the outcome. That's just plain old unobserved confounding, like the kind of which we fear in any observational study. Cool. Kirk.
Whatever makes people take up smoking.
U1. So if X is smoking, and U1 might be, say, like a genetic predisposition for addictive behavior or something like that. And if we don't measure that gene, then we might be in trouble if that gene additionally, perhaps indirectly, affects my outcome. Right. This is so. I love this example. Thank you. It actually grafts onto a really famous example in the smoking controversy. So R.A. Fisher, one of the great founders of statistics, was an incorrigible smoker. And once public health type started saying that, perhaps smoking is not so great for you, R.A. Fisher doubled down and said, maybe smokers are just selected for an unobservable characteristic that makes them simultaneously more likely to smoke and more likely to develop lung cancer. The tobacco industry was deeply grateful for this argument. And it apparently turns out that such a gene exists, but the effect is like minimal. Although I'm not an expert in this, it's just sort of a stats teaching thing. So yeah, what if X is smoking, Z is lung cancer, Y is mortality, and U just happens to be this unobserved factor that creates an artifactual association between smoking and death, even if smoking doesn't cause cancer. If we really believed that this factor existed, then the association between smoking and mortality would be immaterial to tobacco control efforts. It would just be the kinds of people that do smoke happen to die early too, but not because of smoking. Rather, it's because they all have this factor U1. Cool. All right, are we on time? We're decent on time. Let's, Michael, please.
I lost the amplification of your voice.
Oh, yeah.
Oh, really?
Still okay,
Hmm.
but I don't know if everyone can, and I wonder if we can fix it.
Oh, battery is red here. It's on but red. And now it just,
Do we have any extra batteries in the room?
the light, the light just went out on my mic.
Hopefully somewhere we have some batteries. Maybe I can just, don't take it off, just take this part.
Cool, thank you. Eric.
What do you do when someone, so that tobacco example, like maybe there's this view, like maybe there's this, someone proposes this without any reason for it. Like they haven't like thought they discovered it. They're just exploiting something that is true about the statistics.
Right.
What
do you do?
Subvert the model.
That's right. What do? You need to develop norms of discourse. Paul Rosenbaum, a co-inventor of the propensity score and a famous statistician at Wharton, wrote about responsible and irresponsible criticism. Right, so we've discovered that it is never possible to empirically rule out unobserved confounding in a one-shot study. Therefore, a critic can always come along and say, well, but couldn't it be that there's an unobserved confounder that you haven't taken into consideration? And this question has an unambiguous answer. The answer is yes, it could be. But that's irresponsible criticism in as much as it's not backed up by reason. So if we've drawn this DAG for a process that's been studied by science for 3 generations, and there's not just associational evidence but some experimental evidence for some of these links, and maybe in the smoking story there are actually biomedical pathways that are very well lab documented, then it's reasonable, according to Rosenbaum, to ask the critic to cough up good reasons. And I think in scientific discourse, this is a very much accepted norm. In politics, it's clearly not an accepted norm, It's like, what could U1 be? U1 could be Noah's flood. What about original sin? What, couldn't it be? And it's possible, and scientists can't rule out that this exists. Yes, true, but perhaps not responsible criticism.
And obviously there will be cases where a lot of people have a strong intuition about what the U might be.
Sorry, what's this? Sorry, never mind. So yeah, some people have strong intuition, right? And then, it depends. I mean, so and then the smoking community, and I know there's some people in the room who know this better than I do. Fisher became a real problem for public health. But you couldn't just dismiss him because it was R.A. Fisher, like a giant. If I'd piped up and said, "Oh, what about this gene?" It would have just laughed me out of the room. In other words, you would have used, sociological processes of, status and authority to settle this issue. But that's what it sometimes comes down to.
Do we know what he died of?
And I don't know what he died of. Do you? It was not lung cancer. Okay. So then there's just, I'm digressing now. Here's an interesting fact. Among 90-year-olds, heavy smokers have a longer life expectancy than non-smokers. Among 90-year-olds, African Americans have a longer life expectancy than white Americans. All counterintuitive, right? But they're selection dynamics. Right? If you survive to age 90 despite a history of, chain smoking, well, you've just been selected on extraordinary robustness. Heavy smokers who live to 90 are truly special. So, of course, they live longer. So something's peeping here, and
Someone's on the way with the new battery.
okay, cool.
I don't know what the buzzing is. So.
All right, good. Well, as long as it's not a fire alarm or something, I think we can move on. That's cool. Thanks. Oh, there's. Hey, Michael. Okay, thank you. So we got this
battery at lunch.
and we have like intermittent buzzing in here through the intercom.
Really?
So we don't know what it is.
Okay.
Buzzing 30 seconds before you open the door.
I
But
replaced the
perhaps-
battery at lunch. It's what throws me.
Funny, right?
You know, it's a battery. You never know what it's going to do.
Yeah, okay.
We're back?
It's green.
Yes. Well,
We're
it's
good.
you can read it here in the LEDs.
Uh-huh.
That was peculiar.
Cool.
Okay, I'm sorry.
Thank you very much.
Sorry that happened.
Uh-huh. Okay. Responsible and irresponsible criticism. Yeah. Like, every causal inference is conditional on a theory of data generation. If somebody doesn't believe your theory of data generation, they really have no reason to believe your conclusions, usually. Sometimes, of course, we can modify the causal model and still find out that the same conditioning set gives us identification. That's lucky. But yeah, that makes it hard. I should also think it makes it a lot of fun because, it's challenging to think about where the data come from. And various fields have different traditions of how they engage theory construction. And that's really interesting to study. Good, so I want to do one more example here. I want to ask you to apply the adjustment criteria for the total causal effect of T on Y. Is the total causal effect of T on Y identifiable via adjustment?
This may be silly, but I only care about paths where T is on one end, right?
Yes, so all paths start at T and end at Y. Now we need to separate out the causal from the non-causal paths and ask if we can block all the non-causal paths without blocking the causal paths. Effect of T on Y. Signal me when you think you have an answer, please.
Just to clarify,
Please, Thomas.
you're asking if it's possible by some set of variables to be conditioned or not.
Exactly. I want to know if there's any set of variables that I can condition on to block all non-causal paths while keeping the causal paths open. That's what it means to identify the causal effect of T on Y. Thank you. Hands up if you have an answer. Cool. Who thinks that the total causal effect of T on Y is identifiable? Who doesn't? Okay. Great. Well, who wants to try it? Oh, sorry, I should say the answer is yes, it's identifiable. So, Randall, you've...
I don't know if this argument is right, unless I'm missing a path. The causal paths and non-causal paths don't share any nodes,
Very good.
which means I can leave everything open on the causal paths and do whatever I want on the other ones, including block them all.
Very good.
So we don't have any of those
But-
sticky issues with, like the Z1 we had last time, that was on some causal and non-causal paths,
Mhm.
was always finicky.
Very efficient, very efficient. So let's go through the exercise completely. So perfect. Okay, so let's divide the causal from the non-causal paths. There's only one causal path from T, C, Y. Then there are three non-causal paths. T, A, B, Y, T, X, U, Y, and T, X, D, Y. First, we need to block all non-causal paths. Can we do that? Well, what about the first path? How can you block that? Kirk? No. It's the one thing you're not allowed to do.
I'm not allowed to do that.
No, because A is a collider.
Oh, right. Condition on B.
What else could you?
Oh, wait,
Condition on B then, that's right.
You're tricking us.
Or? Huh? What? No, I'm not
collider
tricking.
is already blocking.
Right. So the non-causal path TABY is blocked without conditioning on anything. Huh? It's blocked because you don't condition on A. It's also blocked. Or do you want to engage this path? No. Okay. Well, try.
Well, you said A is conditioning on A is the one thing you don't want to do. But
That's right.
Condition on B as well.
Ah, conditioning on A and B is okay. Correct. So let's interrogate this path again. TABY. A is a collider. If you don't condition on the collider, the path is blocked. B is a non-collider. If you condition on B, the path is blocked. And if you do condition on A, then you must also condition on B. Again, I would love to have a board, but anyway. So there are three ways to block this non-causal path, including not doing anything. Now, what about the other two? Well, the other two non-causal paths go through X. X is a non-collider on both paths. Hence, conditioning on X alone is sufficient. Indeed, conditioning on X is necessary because it's the only way to block the path via U. So, how can we identify the total causal effect of T on Y? First, you have to condition on X. Second, you could, if you wanted, also condition on D and B. And you could even condition on A if you also condition on B. Do you guys want me to just pull up another document and write this out? Or is this, okay, good. Thomas.
Conditioning on X the only way to block the path through U? Why can't you condition on U?
Because U is unobserved. Yeah, good. Questions about this? You guys are good. All right. Now, yeah, please, Thomas.
Is it that you always use U when you intend with unobserved? Because
Yeah.
it's not just that it's out there and things
Because-
flowing away from it. You would also do that sort of.
Yeah, I mean, whatever you would do, however you want to define the variables, right? I use U because it's such a beautiful abbreviation for unobserved. You know, if I was an economist, I might always call this epsilon or little u or something. I mean, U. Okay, turns out the adjustment criterion is complete. It's complete for adjustment in the sense that the adjustment criterion detects all and only those sets of variables that identify the effect of T and Y by simply conditioning on these variables. Put this differently. If you want to identify a causal effect by just conditioning on a bunch of variables, the adjustment criterion unambiguously tells you which variables you must control for, which variables you can control for, and which variables you must not control for, and any combination thereof. In that sense, the adjustment criterion is complete. Now, since most observational exercises in causal inference boil down to figuring out what you should control for, the adjustment criterion gives a complete answer. Indeed, this is, please.
In the previous one, were we going to learn something different if we went through the X on Y scenario?
Oh, I forgot about that. Yes, let's do that. That's going to be good exercise. Do you want to? Good. Okay, so now, same data generating model, different question. Thank you. Can we identify the total causal effect of X on Y? Well, first let's find the causal paths, and then let's find the non-causal paths. What are the causal paths from X to Y? There's the one that goes straight through, and there's X dy. These are the paths we need to keep open. Then we have two non-causal paths, xtaby, and that's already closed if we don't condition on A. Secondly, there's xuy. That cannot be closed. No. xuy is open because it doesn't contain a collider, but it cannot be closed because we do not observe the only non-collider on the path. That's too bad. Julian.
So before you said something about like T could be a noisy measurement of X, something like that.
Sure, you can always view it like that. Mm-hmm.
So if you could somehow bring in some sort of proxy to measure X.
Very nice. So if T is really X measured with, but now you're saying that X is,
Like a real world situation where
well,
having some measurement on top of a population can help you get rid of that sort of stuff.
so let me just say that you can use DAGs to represent measurement error. So if these are the true variables in nature, then we could say that, under classical measurement error, that the measured variables all descend from these respective nodes. And then the question would be if we could identify the causal effect of the latent, of the true variables from the measured variables. And generally the answer is no way, unless you have a really strong measurement model. That's what classical structural equation modeling is doing. It's a super sophisticated approach that doesn't just represent the data generating model, but also a measurement model graphically. In order to get traction on that, you generally have to make super strong functional form assumptions. Psychologists do that quite a bit. Economists started a few years ago in various situations. Political science, much of the medical world, the belief is that you measure the truth. Measurement error makes things much more complicated. Laura.
So am I correct that U would be like classic compounding?
Correct. Kirk, please, yeah.
So classic compounding, you just have no idea. I mean, your results are probably nonsense because of it, but you're pretty clueless. Here, you have a clue. It's in your diagram, so does that help?
Well, it helps if you have a budget to collect more data, right? If U1 just happens not to have been collected, but could be collected, well, let's write a grant and collect data on U. Yeah. So in that sense, I mean, this is actually a really important point, and I'm sorry I didn't make it before. We can use DAGs also to plan data collection, right? We could figure out what's the data generating model that the community believes in, and then we could ask, well, what variables do we need to measure? Here in this model, it would be kind of cool because suppose that it turns out that A is extraordinarily expensive to measure. Well, it turns out in this model you don't need A for identification, so just don't measure it. In fact, it turns out that the only covariate that you really need to measure is x in order to identify the causal effect of t on y. So if money is a constraint, let's just collect data on t, y, and x. So, Eric.
Question, though, what you said, like write the grant and measure. But you can either be like, we speculate that U is something, or you can be like totally hidden arbitrary U.
Right.
That only helps for the we speculated something U.
Correct.
Okay,
Yeah.
Is there, this is a poor question, but is there any way in which you can first measure the association of x and y through U, and then kind of subtract that out from your model to figure out the deviation
X
from
and
that?
y through u. So if u is unmeasured.
So there's a spurious correlation between x and u, or x and y through u, right?
Mm-hmm.
And you could like hold d and t constant. You'd be able to measure the.
That's
spurious.
right. That is right. So now, so you want to. This is a good idea. So you could try to quantify the amount of spurious association if you were sure that you got the stuff downstream from treatment X correct. Your theory hinges on complete mediation. It needs to be true in your story that the effects of X and Y is fully mediated by T and D. If we believe that, then we could use a different identification criterion known as the front door criterion that does exactly what you're suggesting. So the idea is, maybe we can't directly estimate the effect of X and Y, but if we can identify each and every arrow that contributes to the causal effect of X and Y, then we could just artfully put these arrows together to get the total causal effect. In linear models, that's straightforward because the path-specific effect of X on Y via D is just the effect of X on D times the effect of D on Y. Non-parametrically, that's not the case, but Perl's developed a non-parametric version of this path multiplication rule. Nice. Michael.
I think earlier you mentioned instrumental variables as a way to help in this. Can you explain that in more detail now that we have some more terminology?
Oh, gee. Let me put it this way. I teach a 2-day workshop on instrumental variables next week in Chicago. And it'll take 2 days. No, the basic idea is easy. If I had a whiteboard, I could do this, but, not here. And yes, we will use, do go to that. That'll pay for my summer vacation. Please do. I think it's a good course, actually. Run through statistical horizons. Yeah.
Completeness criteria, or completeness result that you had on the screen a couple of slides ago.
Yep. Mm-hmm.
If I'm understanding right, this is not completely complete. You said only the due calculus is known.
It's complete for adjustment.
Right.
Mm-hmm.
So what are the other kinds of things that you can do that get captured by the due calculus and don't get captured by adjustment?
Well, one we've just discussed, this front door idea. So here the causal effect of X and Y is not identifiable via adjustment, but it's nonetheless identifiable because we can identify the effect of X on T, X on D, D on Y, T on C, and C on X. Right? We can quantify all of these arrows that together make up the total causal effect. So then we just have to put them together the right way to get the total causal effect. That's different from adjustment because now I've estimated different moving parts and put them together. And then there's a bunch of other tricks.
It's just not easy to say what the complete.
No, I'd have.
That do has to capture.
For that, I would have to go through the due calculus, right? Yeah. So in a while, I'll give you some non-identification results that are really helpful to know. And I will say again, there are precious few empirical examples I am aware of where adjustment fails, but the do calculus still works. Very few exercises have gone through that. Now let's connect this back to where we started. Adjustment and ignorability. So this Spitzer, Van de Waal, and Robbins paper is also great in that it proves that essentially, not quite, but essentially, if and only if, Z satisfies the adjustment criterion for the effect of T on Y, then T is ignorable given Z. So, our original question was, well, I want condition ignorability, but what should be an X? What should I condition on? Oh, the answer is any set of variables that satisfies the adjustment criterion gives you conditional ignorability. And essentially, anytime you have conditional ignorability, the stuff that you condition on gives you adjustment. That's cool, because this is where these two languages meet. Methodological development and causal inference in statistics these days mostly uses potential outcomes and conditional ignorability. Here, we've used graphs, which are really popular in the biomedical world. They're obviously dominating in computer science. And in this result, these two worlds meet. There's another paper that shows the equivalence between DAGs and potential outcomes in a certain sense, but we're not going to go through that. Mm-hmm.
Am I wrong to be really skeptical that we're going to be able to theorize correctly about these problems and draw good DAGs? Because I just feel like you're always gonna miss something pretty important.
That's an empirical question if we do or don't. Right. So on the syllabi, when I teach graduate courses, I always have this disclaimer that you might get depressed in the first few weeks of this class because, I will tell you all these things beaming as something empowering results, and you'll be like, this is not empowering, this is deeply depressing. But that being said, let's not shoot the messenger, especially not me. DAGs just make these problems that exist really clear. Now I think, I can certainly point to a bunch of papers in my own discipline that assert condition ignorability and it's just risible. It's not believable if you think about the data generating mechanism. I can think about other papers in my discipline and other disciplines that very carefully and convincingly theorize a data generating mechanism. Perhaps, so anytime you have sort of fixed rules or, a design element in your study, you tend to gain a lot of information about where the data come from. So one design element, for example, would be that, we know exactly what makes somebody eligible for Medicare. So we're interested in the effect of having Medicare versus not. That's a really well understood process. You need to have the right earnings history. You better be over age 65. And then there are a few sort of side categories, but they also have very clear eligibility rules. That kind of knowledge is really helpful. As I mentioned before, in engineering, if you know how the machine works, wonderful. If you study a biological system about which a lot of basic science has been done, wonderful, right? That's what we were talking about, Kevin. But no, often we really do need to take strong recourse to theory. And it's good to know that, I think.
Is there, similar to a p-hacking thing, is there the temptation often to you produce a DAG using theory, you realize that it doesn't pass the adjustment criterion, and you go, but if I just killed off that one node, it would. And then you kill off that node and hope no one asks about this other thing. and now you're good? Like,
Well, you know, in science, I hope one would get fired for that.
Yeah. Of course.
You know, no, so I think there are some pragmatic answers to that. First, of course, there are, and as we're learning in the p-hacking and harking and in this emerging awareness of the problems of science as usual, we're becoming aware that even humans with great intentions have this capacity for self-deception. So let's try to put institutional boundaries or hurdles into place that keep us from tricking ourselves against our best intentions. One way to do this would be to pre-register every step.
Right. Yeah.
Super.
Yeah.
Great. What else? A second. So a caveat that I have to mention here is we have very little time, so I'm just presenting this as a black and white story. It's either identified or go home. Of course, that's silly. That's not what we do. We know that in practice, every model is wrong. The question is it credible enough for us to base decisions on them? That's an empirical and quantitative problem. To an extent, formal sensitivity analysis can help us to understand the sensitivity of our conclusion to alternate model assumptions. To an extent, within studies help. So if we're in an area where people have paired lots of observational studies with parallel experiments, well, if they always show the same thing, then perhaps in this particular area, we seem to understand the DGP pretty well. And then otherwise, we'll pretty quickly back to just, confidence. Are we confident that we're doing the best we can right now? And then we'll have to trade off our confidence in the accuracy of the model against the cost of being wrong. If we just base life and death decisions on a particular intervention, we'll probably want to be a little more certain about the model than, if we're doing something frivolous but fun. Michael.
You also see cases where you kind of go full loop. You go all the way to hey, we should take this intervention and make the world better. You take it, and then it doesn't play out the way you wanted it to. Whoops, I guess with this new data, it's sort of like an experiment. We can update our DAG, try again.
So I think this happens all the time. Not necessarily with explicit DAGs, but lots of medical interventions that are all the rage. Then, somebody's like, but why should this work? Do a randomized experiment and the intervention dies a quiet death. So there was this years ago, treatment for, what was it, I think ulcers. Open the patient and just put ice packs on the ulcer to freeze the thing. It turns out the people who got this freezing treatment, I hope I'm getting the story right, did way better than people who didn't. Okay, so this became, now remember, surgical procedures don't have to be FDA approved. It's just drugs that need FDA approval. So if you can make a compelling case that, look, the people that I've cut up, they're doing better than the people who didn't, somebody stands to make a lot of money, and people did. But then people ask, what's the mechanism here? Why should this help? They did a blinded trial, no effect. So what was the story? Well, you have to be doing pretty well in order to be cut open. Sick people don't get cut open. In as much as surgeons had a choice in whom to treat and not to treat, it was a selective choice. Not out of ill intentions or bad will. I don't want to stipulate that. I just, it's happened. So glad we could do a trial. They could do a trial. Then in labor economics, this happens all the time too, right? So, as you may know, econometricians have sort of 5 topics that they research, basically. And one of the topics, par excellence, is the question of, if people get another year of education, does that increase their wages? We don't know. Everybody believes it. We know it's true, unless, of course, you go from your master's to your PhD, and you're not in CS, then don't know. But we're pretty sure that more education is good for wages. But there's an entire library on ever more sophisticated approaches to handling ever more sophisticated objections to prior estimates. So yeah, they go back, they circle through, they take into account new objections. Thanks. Okay, so now we have identification. Here's the only thing I'll really say about estimation. If the adjustment criterion is met, then you know that you can recover the average causal effect through exact matching on your adjustment set. And that's a slightly not pretty looking formula. Right, this is just the exact matching formula. Don't get too excited. Usually we can't exactly match on X because X is high dimensional. If you just have one covariate X that's binary, great, then you just need a minimum of 4 cases, right? A treatment and control case within both levels of X. But if you have 10 binary control variables, which in the medical world is basically nothing, and then suddenly you need 2,050 cases to fully saturate each cell. But then you still have one treated and control case per X value. If you additionally have a continuous variable in there, you clearly can't exactly match on X anymore. So very quickly you're pushed from non-parametric estimation to semi-parametric estimation to parametric estimation because you have these empty cells in this cross table that's made up by your X values. And really what semi-parametric and parametric estimation are doing is they're trying to figure out functional forms that connect the populated cells through the non-populated cells. So yes, identification immediately implies a valid estimator, albeit a valid estimator that you probably can't use unless you work for Facebook or Amazon, where data are not an object. So now, okay, so I've allowed myself to digress a little. Oh no, we're going till 5:30, right? Oh, we still got time. I forgot when we took the last break. Are you ready for a break? Good. 10 minutes. 4:25. Well, very, very good. Moving on. I'm going to skip a bunch of things now. So hands up if you've heard the term adjustment criterion outside of this room. Sorry, okay, and what about backdoor criterion? Also not. All right, let me tell you this then. So the adjustment criterion, as you've seen, is new. It's from 2010, but it's really just a much more teachable version of the much more famous backdoor criterion. So here's what that's about. The adjustment criterion gives all identifying conditioning sets, but it sometimes includes variables that aren't necessary. For example, look at this DAG here. You're interested in the effect of T on Y. That effect is identifiable just by the bivariate association because the only open path between T and Y is the causal path. Nonetheless, the adjustment criterion permits you to control for Z. Right? Z does not block a causal path, and it does not open a non-causal path. So you can, but you don't have to. So it turns out that it is never necessary and often harmful to adjust for descendants of the treatment. Here we go. So this is the DAG we've just analyzed before. Here, this DAG, with a lot of descendants of treatment. We know that we need to control for X, right? Because controlling for X is the only way to block these two, what you might call backdoor paths. Right? A backdoor path is a path that starts with an arrow into treatment. Well, what about front door paths? Front door paths are all paths that go out of T to a descendant of T. Well, let's see. Controlling for E, yeah, you're allowed to do that. it doesn't block a causal path, and it doesn't open a non-causal path. What about controlling for C? You're not allowed to do that because C sits on the causal pathway. Right? Controlling for C is strictly harmful. Controlling for D is also harmful intuitively because D is just C measured with error. So controlling for D is not fully going to block this path, but it's partially going to over-control. Finally, if there's a non-causal front door path, then that path will contain a descendant of the treatment that is also a collider. And you definitely shouldn't control for that alone, because here controlling for A might open this non-causal front door path. In sum, it is never necessary and often harmful to control for descendants of the treatment. Gee, that's why Judea Pearl in his famous 1995 paper proposed the backdoor criterion. The backdoor criterion is the adjustment criterion, and it additionally prohibits you from controlling for any descendants of treatment. Good. So that means the backdoor criterion says, hey, these backdoor paths are always non-causal paths, right? Because they start with an arrow into treatment. And they may or may not be open. Therefore, whereas front door paths are either causal paths or closed non-causal paths. So really the only paths you need to worry about are backdoor paths. Good. So the backdoor criterion says, please close all backdoor paths without closing any causal path. And by the way, don't control for descendants of treatment. So that's the same logic as the adjustment criterion, except it justifies why you only have to worry about the backdoor paths. So that's cool. So the backdoor criterion is kind of helpful because often there are tons of front door paths that just get confusing. Here, let's look at this example. I want to identify the causal effect of T on Y. There's only one causal path, no, two causal paths, TBY and TU2Y. But there are a ton of non-causal paths. TU1AB, TU1EY, TU1EU2Y, and then come the front door paths, TU2EY, TU2EU1ABY. So many paths. But the backdoor criterion says, chill, you don't have to worry about anything that leaves treatment. You just have to worry about paths that go into treatment. Aha! That just cut down our work. So now we see all backdoor paths into T go through U1. U1 is unobserved, so you can't control for it. But all backdoor paths have to go either through A or through E. A and E are non-colliders on all paths that go through them. So conditioning on A and E will close all backdoor paths. Thomas.
The statement that it may be harmful.
Mm-hmm.
Is it possible from your DAG to see which ones would be harmful? It seems,
yes.
If my intuition were right, I would say conditioning on U2, even if it were possible, would be harmful on this DAG.
That's right.
But on the previous one, I don't see any harm in controlling for E and D.
Controlling for E is indeed not harmful. I mean, it's going to make your estimate way less efficient, but it doesn't ruin identification. Conditioning for D is not okay because D is a proxy for a variable on the causal pathway. So in a sense, D contains information about C. So by controlling for D, we're implicitly controlling for part of C. And so we're sucking up some of the causal effect. Justifying that from D separation, so it's actually hard to justify the D rule with D separation. I'm not going to do it here, but you can do it. The intuition is that D is, so C would be over control, D is proxy over control.
So nodes
Julian.
descendants don't include the nodes direct children?
Descendants are all variables directly or indirectly caused by a variable. So the children are the immediate descendants. C is a E, C and A are the children of T, and D, if you will, is a grandchild of T, it's a descendant. Okay, so that was the first shortcut. You just have to worry about backdoor paths. Here's another criterion, the parent criterion. So we only have to worry about backdoor paths, and we know that all parents of the treatment are non-colliders. It follows that conditioning on all parents of the treatment is sufficient for blocking all backdoor paths. That's what I call the parent criterion. Conditioning on all parents of treatment on the causal DAG gives you identification by adjustment. Right? Conversely, this means if there's no arrow from U into T, then you definitely have identification. You just need to control for the parents of T. In my paper, I justify this at greater length. These papers are all available on my website, free of charge. Now here's something from Pearl, the weak bow pattern criterion. If you have a situation where the unobserved variable causes the treatment and any variable downstream from treatment on the causal pathway, adjustment will fail. Why is that so? Well, such a variable U will be a confounder, right? It sits on an open non-causal pathway from T, perhaps indirectly to Y. If the arrow from U goes directly into Y, there's nothing you can do. And if the arrow goes from U into a variable on the causal pathway, well, then you'd have to control for a variable on the causal pathway, and we're not allowed to do that. Hence, this kind of pattern, which for reasons unknown to me is called a weak bow pattern criterion, make adjustment impossible. Nonetheless, other criteria might still save the day. In this case here, the front door criterion that I've gestured toward would still enable identification of the causal effect. Finally, we have a strong bow pattern. If you have a variable U with an arrow into treatment and an arrow into a child of treatment on the causal pathway, then all is lost. Even the do calculus fails. That is, in a model with a strong bow pattern, that is, the unobservable has an effect in treatment and a child of treatment on the causal pathway, there is no way to non-parametrically identify the causal effect of treatment. So here are some abstract examples. You know what? Let's do this one. Let's do this. So we want to know the effect of T on Y. Is there a valid adjustment set? And you should feel free to use the shortcuts. Julian. X3 and X4 are sufficient for adjustment. That's right. Can you justify that? What did you use here?
Control or condition on X3 and X4.
But why does that solve all the problems?
Those are the two non-causal paths.
So X3 and X4 sit on all non-causal paths. That's right. That's not a sufficient justification, though.
The
Parent criterion, that's right. X3 and X4 are the only parents of treatment on the causal pathway. Excuse me. X3 and X4 are the only parents of treatment in the causal DAG. Conditioning for all such parents is sufficient for adjustment. That's a quick and dirty shortcut. Are there other ways? So that's just saying that controlling for these two is sufficient, but is it necessary? Let's see. What if I just conditioned on X4? So all backdoor paths go through X4. Can I just condition on X4 and be done? You smell a trick question. You can't. That's right. Laura, why can't I?
Well, because you have the two coming in to X4.
So X4 is a collider.
Kill the blocking, right?
So there is a backdoor path that's M-shaped, right? The M path here. Up, down, up, down.
Right.
That path is closed until you condition for X4. If we just condition for X4, we open this M path. Sander Greenland figured this out and called this the M bias in the 1990s. So in order to kill this M path, we have to condition for X4 because this little triangle path here only goes through X4. It's the only way to block that. Right? This path here can only be blocked by conditioning for X4. But X4 opens the M path. Therefore, we need to additionally control for any non-collider on the M path. It could be X3, X1, X2, X5, it doesn't matter, as long as you condition for one additional variable beyond X4. Of course, you can't condition on X6, right, because that's in the causal pathway. So this is a canonical example from Pearl's famous paper. It turns out you can show like lots of things with this graph. And you're now in a position to see these things. That's really cool. Good. So now I thought, hey, why don't I throw two really hard examples in there too, but we're not going to go through them because this is going to take too much time. I want to get to real examples. I'm just going to give the solution to these, okay? So can we identify the effect of t on y? Answer is no. And you could try to figure out why exactly that is the case. This is an example toward the end of Pearl's book. This suggests that this is not, strictly speaking, a trivial task here.
What is that dash lines again?
Represent confounding by unobserved variables. That's right. So here this means that there is a u with an arrow into w1 and t. Okay. So I'm not going to justify this. I'm just going to say, no, you can't identify this effect. Then there's another exercise. Can you test the null of no effect? But that's like really hardcore now. An example due to Brito. I'm not going to show you how this is done. I'm just going to say, yes, you can test the null. No, you cannot identify the effect. So that's really cool, but no time. Now, let me go through a regression example. I'm anxious to get to the promised real examples. But since so many of you do regression, I think I want to cover this. So here I've advocated sort of a very econ style way of doing causal inference. First posit your data generating model, then figure out if the model is identified, then look at the data. But in practice, we often start by looking at a regression. First we do estimation. Now, if that is what we do, and I certainly do that too, suppose you estimate sort of a straightforward wage regression. You regress log wages on years of education, years of experience, a race indicator, and a man-woman indicator. Once we've done that, we'll be tempted to interpret these coefficients, won't we? Running this regression theoretically would be perfectly fine if we just wanted a prediction model for wages. But lots of people then want to tell stories about the coefficients. That is, they often want to interpret these coefficients causally. Perhaps say that, an additional year of education will increase log wages by beta 1. The question is, under which circumstances we can interpret regression coefficients causally? Well, the circumstances depend on the underlying data generating model. So before we go on, let me note that controlling for a variable in regression is the same as adjusting for the variable, or roughly conditioning on the variable. All right, let's inspect a couple of DAGs. The most naive data generating model treats all variables as exogenous, that is, determined outside of the system. They just fall from the sky. Well, that would be so sweet, because then the association between each and every covariate and the outcome, wages, would purely be due to the causal effect of the variable on the outcome. That would be great. If this is how the world generates wages, then each coefficient in the regression identifies the average total causal effect. Of course, this model is crazy. This is not how the world works. This is how the world works. Not even that. Even here I've simplified. So let's look at this. So here I'm stipulating that years of experience cause wage, for example, through seniority raises. I'm also stipulating that education affects experience. Perhaps more educated people are less likely to have spells of unemployment. On the other hand, sticking out grad school for years and years means less time to acquire experience in the labor market. Either way, education affects experience. Well, education should also directly affect wages through stuff other than experience. For example, if you have professions with licensing, right? So a certain amount of education is just required to move into certain positions, regardless of experience. So that explains the direct effect of education on wages. Then here's where I'm really simplifying. Female likely has an effect on experience, perhaps through baby breaks. But female may also have a direct effect on wages, perhaps through gender discrimination. Finally, we have race here. Race may affect education, say, again, through discrimination, but race also affects education through neighborhood. Right? So we have huge residential segregation in the country. Different neighborhoods offer different educational opportunities. Kids growing up in really impoverished neighborhoods, and that's mostly racial minorities, will get less education because of that. At the same time, there's actually experimental evidence that the employers discriminate on what neighborhood you come from, just by address. Some seem to screen on this. Interesting. Good. Now, clearly this is a more realistic model than the one we considered before, even though you may still argue that I've neglected a bunch of, for example, I say there's no effect of being a woman on education. Well, these days there's a clear educational difference. In the 50s it was that men got more education, now it's women who get more education. And there's probably an effect of female on education. Be that as it may, if we believe that this is how the data were generated, and now we're estimating this regression, how do you interpret the regression coefficients? Turns out you can answer that by just applying the adjustment criteria. So suppose now that in addition to giving you the structure of the DAG, I'm telling you that this is a linear and homogeneous model. So then, we can just run a regression without having to worry about effect heterogeneity. So let's see. What is the coefficient on experience? Well, the coefficient on experience picks up the association between experience and wages after controlling for education, race, and gender. What paths are open between experience and wages after you control for race, education, and gender? Female. Yeah? Say?
Just the causal path?
Just the causal path. The path from experience directly to wages, which covers the total causal effect of experience and wages, that's open. All other paths between experience and wage are blocked by controlling for female and education. You can additionally control for race, that doesn't make a difference. That's awesome! Beta 2 identifies the total causal effect of experience and wages. That's really good news. What about the coefficient on gender? Sorry, female gender. Apologize. What about that? So again, the regression coefficient on gender captures the association along the open paths between gender and wages after you've conditioned for the other control variables. So what paths between female and wage remain open after you control for race, education, and experience? Just the direct arrow. That's right. So beta 4 only captures the association that flows from female directly to wages. This indirect effect is controlled away by controlling for experience. Hence, beta 4 is not a total causal effect. Beta 4 is a direct causal effect, net of the effect of gender on experience. Okay, so beta 4 is not a total causal effect, but it's at least still a direct causal effect. That's really good. What about the coefficient on education? Again, the coefficient on education will capture the association flowing along all the open paths between education and wages after controlling for experience, race, and gender. So what paths are still open between education and wage?
And through you.
The direct path.
That's right.
Oh, the direct path, yeah.
So there are two paths open. The direct path from education to wage is open, and the path from education to unobserved neighborhood to wage. So is that a causal effect? Is beta 1 a causal effect? As Eric said, it's not, because beta 1 captures both the direct causal effect of education and wage and the spurious association via U. So beta 1 is biased. Any causal question you can think of, beta 1 is biased for it. Anything left? Oh yeah, the coefficient on race, beta 3. Again, the question is, So the fact is that the beta 3 captures the association flowing along all the paths that are open between race and wages after controlling for education, experience, and gender. What are these open paths? So there's certainly race to U to wage. And that's in a sense a direct causal effect. That's pretty good, right? Look again. Anything else open?
Race through education through U through wage?
That's right. We control for education. Education is a collider on the path from race, education, U to wages. By controlling for education, we're opening this non-causal path from race to wages. Therefore, the coefficient on race does not identify any type of causal effect of race on wages, because it consists both of a causal effect and a spurious association. Okay, so what have we learned? We've learned that these 4 coefficients mean 4 different things. The coefficient on experience identifies the total causal effect. The coefficient on gender identifies a direct causal effect. The coefficient on education gives a direct causal effect plus confounding bias. And the coefficient on race gives a direct causal effect plus endogenous selection bias. Therefore, it is generally a good idea to focus. It's a bad idea to tell stories about every regression coefficient. It's a much better idea to hope to imbue at least one of the regression coefficients with a causal interpretation. And you can decide the interpretation of a regression coefficient by using the adjustment criterion relative to your presumed data generating model. Kirk.
Regarding the direct effects,
Mm-hmm.
so you just said that we have a direct effect between, say, education and wage, or race and wage, conditioning on the stuff that's in between it, no problem.
So these direct effects contribute to the coefficient, but they're also spurious paths that contribute to the coefficients.
But is it a problem, let's just focus on education.
Mm-hmm.
Is it a problem that we say we condition on experience?
Well, it depends on what you want to know. If you're interested, the real problem with education is the confounding via U, right? That just adds the spurious association. But it is conceivable that somebody might want to know the direct effect of education on wages net of experience. In that case, you really would be interested in quantifying this arrow. However, in this model, you can't do it because the coefficient on education doesn't just capture the direct causal effect, it also captures the spurious association that goes along the non-causal path with U. Yeah. Yay. Okay. So even in fields where you start with a regression, you can still use DAGs to figure out how on earth you should interpret the estimated coefficients. Estimating regression is easy, interpreting regression not so much. But here we have a machinery that gets us far along the way. Good. I want to close with a few real examples. These are all examples of selection bias or collider stratification bias. The goal here is to marvel at how DAGs render complicated problems eerily transparent. I must have felt really good when I wrote that sentence, but I mean it. So, all of the examples are going to turn on the presence of colliders. You know what colliders are. We remember that conditioning on a collider induces an association between its immediate causes. We also remember that conditioning on a descendant of a collider is qualitatively the same as conditioning on the collider itself. With that, conditioning on a collider anywhere in the social, in the DAG, in the process, can create bias. Conditioning on the outcome or a post-outcome variable can create bias if the variable is a collider. Conditioning on an intermediate variable can create bias if the variable is a collider. Indeed, even conditioning for a pretreatment collider can create bias. So I'll just give you a bunch of examples now. Let's start with conditioning on the outcome or post-outcome collider. So here's a stylized example that was first analyzed by Hausman and Wise a number of years ago. So suppose you have a randomized experiment where you randomize education. Okay, perhaps it's a job training intervention. You want to know the effect of education on income. All is well because this is a randomized experiment. You could just look at the association between randomized treatment and wages and be good. But in this particular study, the New Jersey income maintenance experiment, for some reason, the analysts were forced to truncate the outcome. They were asked to look at the effect of treatment on people who stay poor. Poor in the 1970s meant earning less than $5,000 a day. Now, what does that do? Well, look at this. Here I've written out the error term on wages. And then it becomes immediately apparent that the outcome is a collider between treatment and the error term. Truncating the outcome is the same as conditioning on it, right? We're introducing information about the outcome into the analysis. And thus we're inducing an association between treatment and the error term. That is too bad. Bias. Okay, let's not truncate outcomes. Hausman and Wise provided an exacting analysis of this and struck fear into the hearts of social planners. That's good. We can draw a DAG. Similar story, funner context. Suppose we're interested in the effect of commercial success on critical success in rock and roll. So, Rolling Stone magazine, as you may know, is like the premier music magazine, right? If Rolling Stone, particularly in the 60s and 70s, if Rolling Stone said that this, I'm so square, I don't even know what Rolling Stone would have said. If they'd given their seal of approval to a particular rock and roll recording. Right, yeah, no, I'm searching for the word, but all I can hear is my grandfather, whom I asked, but you don't like anything that's non-classical? What about the Beatles? And he goes, insolent noise. Okay, so now we're interested in whether topping the Billboard charts leads to critical success. And so the Rolling Stone magazine has this awesome, very rock and roll list of the 500 greatest albums of all time. Like, that is so rock and roll. And we're asking, does topping the Billboard chart help our album get into the Rolling Stone 500? Well, I think there's good reason to presume that it should, because the Rolling Stone editors can't possibly have listened to all of the tens of thousands of albums ever released, right? But they'll definitely know the chart toppers. So by that, and if you then, I don't think you have to be, well, it goes, the Rolling Stone folks, you don't have to be a neoliberal shudder to perhaps believe that if tons and tons of people like something, perhaps it's not terrible. Okay, but who knows? Who knows? So that's the causal question here. The finding of the study that did this, there's a couple of studies, was a dramatic and counterintuitive result. Topping the Billboard chart is one of the best predictors for not making it into the Rolling Stone 500. So we can immediately post hoc a story here to say, oh wait, it's the Rolling Stone. They're completely snooty. Of course they hate. You know, as soon as a rock and roll album becomes popular, it's pop. So they can't make it into the list. Credible post hoc, right? But let's look at the design of this study. Just like the Rolling Stone editors, the analysts didn't have a list of all albums ever released. So instead they did something that's quite common in the study of success. Commercial, political, cultural success. They compared the most successful cases to slightly less successful cases in order to determine what sets them apart. So they included all the 500 albums in the Rolling Stone 500, right? Easy, because you got that list right there. And then they also included a bunch of albums that did not make it into the Rolling Stone 500, but that won other accolades. For example, topping the Billboard chart. Okay, that means that the sample is now selected as a function of the treatment and the outcome. And now what do? Well, we analyze the sample. That is, we're conditioning on the fact that we have observed the variables. So the cases. So what happens, you've seen this coming from a mile away, conditioning, so selecting our sample means that we're conditioning on sample selection, and that induces an association between Billboard topping and Rolling Stone via this path, even if there's no causal effect of B on R. Indeed, this particular story of sample selection even allows you to sign the bias. Right? So Billboard topping necessarily leads to inclusion. So this arrow is positive. Rolling Stone 500 necessarily leads to inclusion. This arrow is positive. Well, let's think about this. If my album didn't win the Rolling Stone 500 but is in the sample, what must be true? I had a chart topper. Conversely, if my album's in the sample but didn't top the Billboard, well, it must have won the Rolling Stone 500. So this sampling technique induces a strictly negative correlation between topping the Billboard and winning the Rolling Stone 500. Now, that doesn't tell us the true sign of the causal effect here, right? It's still possible that that topping the Billboard chart has a negative causal effect on Rolling Stone 500, because Rolling Stone editors are snooty. But given that we know that we've introduced a negative artifactual correlation here, I'm a lot less willing to let go of my initial hypothesis that topping the Billboard actually helps with inclusion. It's an empirical question that I can't solve because I don't have all the albums ever released. Good. Now, yeah.
I like the story. What happened from 2004 to 2011? Was that just a redo of the same methodology, or was the 2011 paper?
I think different sample.
In the
No. It's a slightly different question. Honestly, I don't fully remember which one I'm mostly drawing on here. In the 2011 paper, the authors note that this is a counterintuitive finding, and they have a footnote that says one shouldn't overinterpret this coefficient. And I fully agree with them. And we're given a reason here. The structure of this problem is something that medical scientists usually see a lot quicker than social scientists, because what we've done here is we've botched a case control study. Case control studies is something that you get taught in the first epidemiological methods course in graduate school, but it hardly ever shows up in social science statistics training. There's a pity. Case control study are a way to study rare outcomes. Right? If you study a rare outcome, you just have, so like a particularly rare form of cancer, you have to include all the so-called cases, all the cancers in the analysis, which means that you've selected on the outcome. Well, it turns out it's okay to, selecting on the outcome ruins non-parametric identification, but it still enables causal inference on the odds ratio scale. But there is a golden rule of case control studies. And that rule says that if you select on the outcome, you can't additionally select on the treatment because of this. So here we have an example of a botched case control study. And that design is not infrequent in studies on the determinants of success. Pardon me, huh? So here's the same thing from a business perspective. Suppose we're interested in product diffusion. So lots of scholars and especially folks in marketing are interested in estimating how quickly a product diffuses the market. Right? So for example, drugs might get introduced first to a bunch of trend-setting doctors, and then the hope is that the doctors recommend the drug to their buddies, and so it percolates through the market. Viral social network marketing campaigns work like that too. And so people with tens of thousands of so-called friends on Facebook can make a pretty penny by agreeing to push certain products in their feed. Good. So the specific question we're now asking as organizational scholars is one about path-dependent diffusion. We want to know to what extent the number of previous adopters influences the number of subsequent adoptions. So Y here, Y sub t is the number of adoptions at time t. And we would think that if more people adopt the product at time 1, that should have a positive effect on new adoptions at time 2, right? And we want to estimate the strength of this effect. Problem is that most products never enter the database because most new products die upon release. So instead, at least it used to be the case that only reasonably successful products start to get tracked, right? Once they've taken a certain share of the market or hit some annual revenue goal or something, then people take notice and they collect data. Well, what does that mean? So suppose that sample inclusion, so the fact that the product makes it into our database in the first place, is a function of how many people have adopted this product already. Well then, we would have an arrow from adoption into sample selection. We're analyzing our sample, and again, we're going to strictly underestimate the strength of this diffusion effect. Denrell and Kovac demonstrated this fact by simulation 10 years ago, and we draw a DAG. Okay? You should see that this is the exact same structure as the Rolling Stone example. It's the same structure because we're interested in the effect of Y1 and Y2, and we're selecting on both. We're selecting both on the treatment and on the outcome. Cool. Where are we? I'm going to skip the motherhood wage penalty. That's sort of a classic econ example that's also really nicely illustrated. Let me talk about, so far I've talked about the danger of selecting on the outcome or a variable that descends from the outcome. Now I want to talk about the danger of conditioning on an intermediate collider. And here, so you can look for yourself, informative censoring, proxy control, beautiful examples. Let's skip right to one of my favorite examples due to Tyler Vanderweel a few years ago. This is the famous birth weight paradox, which, hands up if you've heard about this term. Okay. It's a smoking thing, say yes, I know you have. Okay, so here's a graph, okay? S says, so this is a story now of neonatal mortality right after birth. S tells me whether mom smokes or not. And for argument's sake, let's suppose we've randomized maternal smoking because, I don't know, somebody allowed us to. So this is a randomized experiment. We've randomized smoking, right? Best case scenario, at least for the researcher, though not for the mother. Then we think that smoking causes neonatal mortality. Smoking also causes low birth weight, and low birth weight causes mortality. Furthermore, we think that there's other stuff that confounds the effect of low birth weight and neonatal mortality. For example, birth defects. Kids with birth defects are lighter, they get born earlier, they have higher risk of neonatal mortality. Good. Now here's a famous finding. It is well known that smoking is associated with increased neonatal mortality. The kids of smoking mothers just run a higher risk of death than the kids of non-smoking mothers. Pretty big effect. But among babies with low birth weight, smoking is associated with lower neonatal mortality. Let that sink in. Among low birth weight babies, maternal smoking is associated with less mortality. So that begs the question, is there perhaps effect heterogeneity? Is smoking protective of low birth weight babies? Because if that was the case, we should tell all mothers whom we know are about to give birth to an underweight baby to start smoking real quick. Or could this be an artifact? Ooh, let's see. By the structure of this DAG, the second fact here, conditions on low birth weight. Can't highlight this, all right? What does that do? Conditioning on L means that we're conditioning on a collider along the non-causal path from S to L to U to Y. Hence, even in this randomized experiment, the conditional association between S and Y given L is not a causal effect. Rather, the conditional association between S and Y captures the direct effect of smoking on mortality given low birth weight, plus this non-causal spurious association via birth defects. So here's a story. Let me see if I can get this together. Hang on, how does this go? It is late in the day now. Yes. If mom is smoking, but she gives birth to a normal weight baby, well, then that means that the baby does not have birth defects, right? Because for the baby to be normal weight, despite mom smoking, that means that the baby otherwise has to be healthy. However, if the mom is a smoker, and has a, no, if the mom is a non-smoker, but has a low weight baby, that's it. If mom is a smoker, but has a low weight baby, that means the baby must be sick. If mom is a smoker and the baby is normal weight, that suggests that the baby is healthy. Well, okay, so that's given you an association between smoking and birth defect conditional on low birth weight, right? Being normal weight to a smoking mom suggests that the kid is pretty healthy. Being low weight, that's it. That's the story. So that explains it. Among babies with low birth weight, the kids of smoking mothers are likely unusually healthy, and the kids of non-smoking mothers are likely unusually ill. So that's it. If this arrow here, the effect of birth defect on mortality, dominates the effect of S on Y, you can flip the sign. Now, there's no empirical proof that this is indeed the case, but from my reading of the literature, this is a pretty compelling story here. Yeah, Laura.
So I thought it was, wait, so are you telling what you think it really is, or you're just saying what people may think?
No, so van der Waal proposed this graph to explain the birth weight paradox and to explain it as an artifact, right? So here, this story suggests that the observed positive association between maternal smoking and survival among low birth weight babies is an artifact of conditioning on a mediator,
Right.
rather than an actual protective effect of smoking.
Yeah, because if you're a low birth weight baby from a smoking mom,
Mm-hmm.
you probably are genetically okay. But if you're a low birth weight baby from a non-smoking mom, you're more likely to not be genetically okay.
That's right.
Or
So,
for there to be something else going on, which would have a higher risk of death.
right. So the U here in your story is just genetic predisposition to death.
Well,
Mm-hmm.
yeah.
Mm-hmm. Yeah, it works too.
I mean,
So van der Waal, so read the van der Waal paper. He's more eloquent than me. I think I botched the explanation. But, well, I rescued it in the end, but in the beginning I botched it. Van der Waal discusses a number of possible risk factors besides birth effects here. And, yeah. Julian.
So the whole situation would be that someone may have done some statistics and then came up with that second bullet point. And
Yes, the second bullet point is a fact.
Right. And then if two people, one of them didn't have this framework, they would be spouting off incorrect science.
Well,
And someone else who had the correct framework can kind of explain it.
Well, so there are two competing models that we're negotiating. One model is the one we've analyzed. The other model says, oh no, there is no U. So the conditional association between S and Y given L is the direct causal effect. And the question is, which model is more credible? And it seems to me that the consensus is that the birth weight paradox is not due to an actually causally protective effect of smoking on low birth weight babies. It is an artifact of selection. Well, I mean, first of all, Julian shouldn't trust anybody over 30, but we know that from Rolling Stone. Yeah, okay. So this is a general problem in mediation analysis. Many a fine randomized experiment has been ruined by additionally controlling for mediators. The NIH won't let you get away with that anymore. So it's now well known among experimenters, or at least the ones that compete for funding, that as soon as you control for a mediator or any post-outcome variable really, you might lose causal identification. And the reason for that is transparent here. Even with a randomized treatment S, the mediator has not been randomized and hence is likely confounded by something unobservable. Conditioning on the mediator will induce a spurious association through the unobserved risk factor into the mediator and the outcome, hence making these conditional associations uninterpretable. A lot of work's happened in the last 10 years on mediation analysis, and the same van der Waal has published a wonderful book on causal explanation, 2015, which I strongly recommend for anybody interested in mediation analysis. Also uses lots of graphs, uses counterfactuals. It's a great book.
Do the respective journals just take that as like one test, like before they, the editor says, yeah, we'll publish this one? Like, do they say, did they control the mediator?
It depends. I think any efficacy trial that makes causal claims from a mediation analysis is for sure, I hope, not going to get into a good medical journal. But no, there are plenty of examples of this happening. But in the last few years, I've really seen sort of a much greater awareness of this problem. In the social sciences and business, this kind of stuff still happens a lot because we come from a world where we just run these regressions with 20 covariates, and then we tell stories about each coefficient. Well, almost by design, some of these variables are going to be mediators. And hard. Okay, let me close by justifying why it's not always safe to control for additional pretreatment variables. So it's standard advice to just throw in the kitchen sink into your regression or your matching model. The general idea being controlling for more is always better than controlling for less. And there are various reasons why that's not true. I want to highlight a particular one here. So here's the basic problematic structure, again due to this famous paper by Pearl. The Pearl 95 paper has so many great structures that there's certain things you can show with these structures that he didn't even bother to mention in the paper, like this. So, you're interested in the effect of T on Y. Can we identify this effect through adjustment? Yes, we can, because there's the causal effect and one non-causal path. That non-causal path is blocked by the collider X. So the way to identify the causal effect of T on Y is not to control for X. What happens if we control for X? Yes. We open the non-causal backdoor path. So this is a clear example. We're not controlling for the pretreatment variable X is the right thing to do, and controlling for the pretreatment variable is the wrong thing to do. Right? That proves that it is possible to make things worse by controlling for pretreatment variables. Good. So then Winship and I wrote this paper with lots of examples of selection bias that you can also get from my website. And then we get back the reviews after an interminable time. And one of the reviewers said, this paper is great. Unfortunately, it's never harmful to control for pretreatment variables. So please just strike that from the paper. We're like, that's kind of one of the three main points of the paper. Thank you for not rejecting out of hand. Also, you're wrong. So then the reviewer came back very reasonably and said, fine. Do you have an example? So a year later, yes, there is an example, and it is called network analysis. So in much of network analysis, we're interested in social contagion. For example, if you're a political scientist or you're in a sort of a persuasion marketing campaign, again, where you want to sort of convince like a small group of people that your product's great and then they should go out in the world and tell all their friends. Right? We want to know if influencers actually influence people. So, now we're going to draw the DAG, and this is the most complicated DAG yet, but that's okay because we still got 5 minutes. When you're dealing, so far we've implicitly assumed that we have independent observations. In social networks, of course, you don't have independent observations. So now we're going to draw our random variables separately for each individual, because my X might influence your X. We need to differentiate between the two. So here we have two individuals, I and J, Igor, at the bottom and Jane is on top. We're interested whether Igor's civic engagement at time t motivates, influences, inspires Jane's civic engagement at the next period. I'm drawing the graph here under the null hypothesis that Jane is totally unimpressed by Igor. Okay? Igor does not influence Jane here. Could there be spurious associations? Why, yes. If we do inference in causal networks, we don't just have to worry about the individual characteristics of Igor and Jane separately. We also have to worry about the structure of the network and how it came to be. And that's F. F is the friendship tie between Igor and Jane. Now, humans don't pick their friends at random. Humans are homophilous. That means we tend to be friends with people who are just like us. And nowhere is this clearer than in marriage. So this old story about opposites attract, not true on average. People tend to marry and befriend people who are just like them, down to things like the angle at which the nose hits the skull, the distance between the eyes, non-consciously smellable pheromones, and the overt stuff, of course, of religion, ethnicity, socioeconomic background, education, region of origin, all of that. We befriend people who are just like us. Cool. So now suppose that we have something called latent homophily. The factors that affect friendship formation are unobserved, but they're also affecting the treatment, and here they're affecting the outcome. In our case, you might be altruism, right? So if Igor is an altruistic person, he may become friends with Jane because she's also so wonderfully altruistic. So that justifies the errors from altruism into friendship. But altruistic people are just more civically engaged anyway. So, at this point, is Igor's behavior associated with Jane's behavior? Yes, it is. It is because we're conditioning on F simply by posing the question, what's the effect of Igor on Jane given that they are friends? Right? You might select a bunch of friendship dyads, boof, there you've selected on friendship. Or you may have dyads and non-dyads, in which case you would estimate the effect of YI, of Igor's behavior on Jane's behavior after controlling and interacting for F. Yeah, so the story is clear now. Conditioning on F opens the non-causal path from Igor's behavior via their altruism to Jane's outcome. Simply put, if Igor, goes and votes every time and is active in his neighborhood association, that tells us that he's an altruistic guy. Well, that also tells us that his friends are likely altruistic, while altruistic people vote and are active in their neighborhood associations. Charlizy and Thomas, who first drew this graph, went so far as to say that homophily and contagion are generically confounded. And this is a problem in social network analysis, a real problem, because few of us think, so we're all usually focused on modeling either the treatment or the outcome, but when we look at social networks, we also need to model the process of network formation. Of course, also the process of tie dissolution. That's just not typically done, but it has to be done, because otherwise we'll find these spurious associations between people. That's an issue. So again, this is due to Charlizy and Thomas. The only thing we added was to point out that this is not confounding. This is selection bias. The problem here is not that we don't control for stuff, it is that we control for stuff. Good. Good news is Greenland thinks that this bias is generally going to be small because it has to traverse such a long pathway. But there's no guarantee that it's small. Well, variable selection. You've seen this coming. I've said before that the machines can't save you. Arnold knew this a long time ago. So what's variable selection? Variable selection tools can only look at associations and then make recommendations about what variable to include or not to include. One such criterion is based on the associational definition of confounding. These conventional algorithms search for what they think are confounders. And confounders are usually defined as a variable C that's associated with treatment and the outcome and temporally precedes T. Conventional advice is you should control for all variables that precede treatment and are associated with treatment and the outcome. Note the purely associational language here. Not safe. Here, this is the same DAG we've already inspected. We can construct examples of variables C that precede treatment, are associated with treatment, are associated with the outcome, and yet you should not control for this variable. Again, not controlling for C identifies the causal effect of T on Y. Controlling for C botches the analysis. So, how bad is the bias? Neither the size nor the direction of the selection bias can generally be predicted without further parametric constraints. Neanderthal and Ogburn have a paper in arXiv that gives analytic results for binary variable systems. These are really complicated analytic results, but they're analytic results. Now, in certain systems where you have a variable that you kind of both need to control for and not control for, Greenland says control for it because confounding will dominate selection. That's reasonable, but not guaranteed. But most importantly, we need to remember that all studies are biased. And when parametric theory to rule things out is unavailable, a formal sensitivity analysis might indeed be advisable. So if we can't be sure that our DAG is true, if we can't be sure that we've measured and controlled for all variables we had to, let's just do a formal sensitivity analysis that goes through various scenarios and computes how bad the bias would be if these alternate scenarios were true. Okay, in conclusion, we've spent the day learning about causality and about DAGs. We started by reviewing the dominant definition of a causal effect as a difference between potential outcomes, and within an hour had convinced ourselves that you can get causal estimates from observational data if you have conditional ignorability. But what is conditional ignorability? It's really hard to say. We know that we need it, but we don't always know how we can defend it. For that, we went to new notation and learned about directed acyclic graphs. Directed acyclic graphs have three purposes. One, they allow us to notate the qualitative structure of the data generating process. That is, they allow us to cast all of our knowledge about the world in a single concise picture. Once we have this picture, we can link our assumptions to data and ask, what variables should be associated and what variables should be independent if my theory were true? That helps us to test the model, because if we find associations in the data that shouldn't be there if our theory were true, then we know that our theory is wrong. We can go back to the drawing board. Now, once we've convinced ourselves that we're reasonably sure about how the data were generated, we can more specifically ask which marginal or conditional associations that could be computed in the data actually identify a causal effect. And we've learned that one way to identify causal effects with graphs is to close all non-causal paths while leaving all causal paths open. Well, wonderfully, those adjustment sets that make that happen are the very sets of variables that give us conditional ignorability. So that's how we've linked these two worlds. In the end, of course, this is hard because so much rests on a strong understanding of the data generating process. Garbage in, garbage out. But at least we now know what to look for, and we've seen certain common problems that pop up in all sorts of fields: political science, sociology, public policy, public health, and viral marketing. I believe that being able to take substantive stories about data generation, process knowledge of folks in the trenches, being able to take that information and to map it onto these pictures is extraordinarily helpful for quickly recognizing both problems and opportunities in observational causal research. Clearly, there's more to be said. I encourage you to go to the book stand downstairs, and there are 2 books by Judea Pearl that are not so technical. Good reads, A Primer on Causal Inference, and the Book of Why. Those would be great places to read more. You're, of course, also welcome to check out my papers on my website that track much of the material in this course and additional stuff. And I encourage you to take these lessons and apply them to the world to improve it. I enjoyed very much spending time with you today. I was thrilled by your active participation. I hope to see you around. Thank you.